So let me first of all welcome you all to this masterclass about advanced computing, in particular by emerging HPC technologies. So the way it is, I'll be the moderator for this session. My name is Pedro Alberto. I come from University of Coimbra. Also, I'm involved very much in HPC projects, not only in Portugal as a head of infrastructure laboratory for advanced computing, but as well as in Europe. So I'm participating in PRAISE for a long time, since its beginning. So, okay, so it's a pleasure to me to welcome Dr. Alejandro Rico. But let me, before introducing him, let me just talk, let's say a few words about the subject at hand. I don't know whether people participate are aware or know much about HPC, but anyway, I think just a few words regarding this. So HPC, high performance computing, is now considered a key technology, both for science and industry, such that the future Digital Europe program is one of the three pillars of Digital Europe program of the European Commission. And we are now, I think at this moment, sort of a crossroads in it. So in the sense that HPC is enlarging very much its scope, just beyond the traditional simulations, which require large computing power. And then we are addressing now also some data challenges, and the HPC is very well fit for that, because you can combine computer power with high capacity storage and high performance storage. And this is ideal for many challenges that we face today in data processing. At the same time, Stanzione is join us. Okay, very good. And at the same time, we see that there is lots of new developments, not because only at the run to exascale. Hi, hello. And I was just making some introduction before giving the floor to Alejandro. And yeah, so this is really a very interesting time in HPC, a sort of a crossroads. Computing, data, and new technologies, with exascale, again, challenges as well. So European Commission is highly investing in that, in software and as well as hardware. So we're looking forward to hear about these two distinguished speakers talk about these new developments. So let me first of all, let me for the public, for the attendees, which I welcome as well. Let me just say that you be able to ask questions via the Q&A option in the Zoom menu. So you have a Q&A. I don't know if you have a Portuguese version how it's called, but you can ask your questions, and in as much as possible try to answer at the end of the speaker's talk. Okay. In principle by the speakers if you have time, but let's see what comes out from it. So with this, it's my pleasure to introduce Dr. Alejandro Rico. He's from ARM, but he's doing a lot of research in parallel computing, and especially related with the new ARM processors. He was part of the Mont-Blanc project, which I knew a little bit about because of PRAISE. It was taught very much in PRAISE. And he was at that time at Barcelona Supercomputing Center, which is also a member of PRAISE, and a very active player in HPC in Europe, not only in Europe, in the world, I think. So under the direction of Matteo Valero. So it's a pleasure to introduce him. And so he will talk about his experience and his knowledge about RISC processors. ARM processors. Please go ahead.
Okay, thank you very much. Gonna start sharing my screen. And let me know if you're seeing the right screen or if I should switch it.
Looks good.
Looks good. Okay, you are not seeing my okay. You're saying you're good. Yeah, we can start. Thank you, everybody, for coming to this session. And thanks, Pedro Alberto, for the nice introduction. I think I'm well placed to talk about ARM and HPC in general because I was there since the very beginning. And today I'm going to give you a little bit of history, a little bit of technology, and a little bit of what comes in the future in terms of technology for HPC in the context of the ARM ecosystem of partners. And Pedro Alberto, in his introduction, mentioned that HPC is a very important technology for to solve societal challenges, and that it's one of the pillars from the European Commission to achieve the solutions towards those societal challenges. And I want to start by talking about how I see those societal challenges being defined and being approached globally. And I think those are through the global goals for sustainable development that were introduced in 2015 by the United Nations. These are a set of goals, 17 of them. As you can read them here, I will not read them for you. And each of these goals, at the same time, it has for each of them some specific targets and some ways to measure how successful the progress towards those goals is. And I think that HPC in particular contributes to the progress towards these goals. And I'm going to be talking today about these three that I'm highlighting: good health and well-being, affordable and clean energy, and climate action, and how HPC helps toward these goals. Before that, I want to mention that, of course, ARM is not only a company that produces technology for HPC, but it's the main, let's say, main market nowadays is mobile computing, especially smartphones, tablets, and so on. And it's growing in other areas, HPC included. And of course, it does a lot more towards contributing and supporting the goals than just supporting HPC. Actually, ARM funded a partnership called the 2030 Vision that you can access to the URL that you have there. And it's a partnership with many companies in our industry to be able to tackle big projects. This is pretty recent, and tackle big projects to contribute towards those goals. And I think that's the main strategy from ARM towards doing some big contributions towards the goals. Apart from this, ARM has also been working with organizations like UNICEF on very low power, very high efficient devices that can help towards these goals. One example here, I'm showing this medallion that in certain countries allows, without any batteries, is like you don't need to have any power on it. It can keep a medical record with a medical history for people that they don't even have an identification. They are born in communities in which they don't have ways to keep any type of records, let alone medical history. With this medallion, the medical history is actually stored there, and every time they need some medical care, they can use the information stored there to see what treatments they had in the past, what symptoms or what diseases they had. And it's life-changing for many people. Another project is the SIMPRINTS biometric identification system. As I was saying, many communities, they don't even have ID, and they don't have ways to identify themselves to get certain services. With this centralized, very low-cost device that uses the fingerprints to identify people, they can get access to banking, to medical care, and so on. And the last one that I'm going to talk about, I mean, there are like tens of these examples, but I think these three, I'm showing them because ARM is specifically supporting them, and I think they are good examples for this. There is this device shown in yellow here that it can be powered with very cheap batteries, and it provides information in zones that are in danger, that they may be suffering from war, or they may be suffering from famines or other types, or even they are detached from all other communities. These devices are sent to these places to provide information of maybe how they should be getting out of the situation, or how they can, where they can get help, or even entertainment, maybe stories, maybe also education at very low cost. And here I was showing some examples from the lowest end of computing, very low power, very high energy efficiency, which is something that ARM is a leader on. And this talk is about HPC, which is very large systems, and that's what I'm going to be talking about in the rest of the talk, in which it's also very important to be very power efficient. So in general, HPC and supercomputers are key to help with some of these goals. And here I'm showing how they contribute to this target. And we are suffering this COVID-19 pandemic, and that's why I'm not in Portugal enjoying food and people there, and I cannot meet you guys this time there, and we have to do this remotely. And I wanted to show some examples of how HPC helps towards that. In the US, there was this consortium for using HPC. It has these 87 projects that I'm showing right now. And some of these projects, they have already produced some very good results. Here in the top right, I'm showing the experiments that were conducted in Oak Ridge National Lab, in which they found that this berry-killing storm was a potential explanation for how some of the patients are suffering very different kinds of symptoms and having issues in the whole body in different organs. In Argonne National Labs, they have these models that they are looking at how the virus spreads in communities. And then here I have another example in how this Fugaku supercomputer, which is the fastest supercomputer in the world, and it's powered by ARM technology, and that will be something that I will be talking more about later, has been showing how the virus can spread in certain conditions. And that has been very useful to provide guidelines on what are the right ways to protect and reduce the spread. Another example is affordable and clean energy. I like a lot many of these examples, but I think the wind farm simulation is a great one. You cannot just place these windmills and say how it works and just try and error. These simulations are great to see what is the best way, the most efficient way to place the wind farm to generate the most energy with the least cost. Some simulations also for more efficient batteries for electric vehicles. And one that I think it's very important and we're going to see in the next decade whether it's successful is simulations for nuclear fusion reactors. And there's international effort called ITER, and some of these HPC installations are doing all the simulations for the design of the system before actually building it. And last example, I wanted to talk about how HPC helps towards climate action. There are many examples here. This is some simulations of the air quality. This is from the Barcelona Supercomputing Center called Calliope. And there are simulations on ice sheet and how fast it melts in certain areas like in the Antarctic or in places like Greenland. And then some issues that were very recent in certain areas in the US with these wildfires. there are these methods to predict how fast and in which directions and what would be the reach of these wildfires will be in the upcoming hours. And these models are very helpful to help firefighters to predict what could be the growth rate and the direction of the fires. These kind of simulations in these supercomputers for climate have been growing a lot. And some years ago, they were very focused on just air or ocean, but they have been growing into more specific and more detailed and more precise parts of the Earth. And I want to mention also something that is growing a lot, and it's the use of sensors, like this example that I'm showing here, the array of things that the Argonne National Lab is a contributor to it. These sensors that have all kinds of measurements for air quality, for even cameras for pedestrians, traffic lights, all kinds of information that you can gather with these hundreds, thousands of devices that are out there and can provide lots of data online to models in supercomputers to help also politicians and governments to create policies that help climate. So now that we know how important is HPC and how key it is to address these societal challenges, I want to go a little bit back in history and how ARM, that was zero presence a decade ago in anything HPC, today is the main technology in the fastest supercomputer in the world. This started with some visionaries in Europe, UK. The main partners of this Mont-Blanc project that was mentioned by Pedro Alberto at the beginning were the Barcelona Supercomputing Center that was coordinating the projects at the beginning, ARM and Bull. And this started early, end of 2011. And it was so successful that the European Commission has been renewing the support for this project over a whole decade. And the Mont-Blanc 2020 project, which is the last project in this series, and I will explain why is the last one, it will be finishing in a few months. One of the main targets for the Mont-Blanc project was to deploy clusters, HPC clusters, and I will say what it means, HPC cluster, and to test whether these processors could actually run any HPC code at all, any HPC software stack. And the Mont-Blanc project started with some very little toy clusters, and that's why the title in my talk, and targeted to deploy a larger prototype, which was the Mont-Blanc Prototype. Even before that, PRAISE already supported the deployment of a certain amount of clusters. The very first one was called Tibidabo, and that one was in 2011. And I'm going to give a little bit more details about this one because this one is deep in my heart. This was designed in conjunction with a company, Italian company called Seco. And you had these little daughter boards with this chip that had a couple of Cortex A9 processors. Yes, 5 watts was around the power of this very low power device. And then you would put that daughter board in this motherboard, and then we would put a bunch of them in a blade, and then we would put them all in a rack. And there were 256 nodes like this one. This was a very manual work, and we assembled it in October 2011. It was basically PhD student work. Here I'm showing some pictures of how we actually did it, and this is myself 9 years ago with a little bit more hair and a little bit younger looking. And we did all this by hand, putting everything together, cabling and all that stuff, which was very rewarding experience. And the challenge that was to go and deploy a whole HPC software stack, something that nobody has ever done before on this machine. And we were successful with it, and we could run some applications that through MPI, they scale to the whole size of this machine. Of course, networking was Ethernet, so that wasn't great. Good thing, and the best thing, is that we got some initial lessons learned from this effort, apart from all the enablement for the HPC software stack. And that's why we call this the first ARM-based HPC cluster, because nobody has deployed a HPC software stack on any cluster with ARM processors before. Some problems were that these are non-HPC platforms, only 32-bit addressing, so that meant only 4 GB of memory. These processors don't use Ethernet because in cell phones you don't have it, so we had to bridge that, and all the I/O was just too slow. And of course, when you are running on a phone like this, then I guess it's a problem if you try just to have that processor running continuously, which is something that a cell phone is not doing. So there were some cooling issues, and 24/7 operation was really not something that the system was prepared for. So this is the very first effort, 2011, on deploying one of these prototypes. The next big prototype was the Mont-Blanc Prototype, and this was a little bit more powerful chip. It was on and I'm not sure you can see my video, but if you can, I have one of these here. One of these nodes was just this size that I have here in this frame. And the nice thing about it is that it had a compute capable GPU on it. So we could run heterogeneous codes with the software that runs both on the CPUs and also do some GPU computing with OpenCL. This was a way more professional system. It was assembled with the typical Bull Atos enclosure, and it was just inside those enclosures in which we had a custom blade organization for these kind of very, very small nodes. And this was very useful to also deploy other parts of the software stack that are important, like power monitoring and temperature monitoring and some other parts of the whole stack that are necessary to not only make this work, but also operate it in like you would do for any HPC system. We also scale a bunch of applications. Here you have the reference to the paper in which we show how this was scaling with different codes with MPI up to the 1080 compute cards that we had in these 2 racks. So these are the efforts that were done in the context of the Mont-Blanc 1 project. And as I was saying, this success has been continuing through these multiple generations of Mont-Blanc projects that were focusing on different parts, not that much on deploying prototypes, but more on using this Mont-Blanc prototype to further get further insights and porting applications and testing them on it. In parallel, so I was saying that Mont-Blanc 2020 is finishing, and that's because this set of the Mont-Blanc project created a very strong consortium in Europe that was very knowledgeable on ARM technology for HPC, and that has led to the European Processor Initiative that is fully supported by the European Commission. In this initiative, a new company has been created, which is called SciPearl. And SciPearl is it's based in France, and they are going to be the ones to build the European processor. And they have a roadmap of what they are going to be accomplishing in each one of these years that you see here. The processor is called REA, and there are multiple generations of it. it's going to be using this Zeus core, which is a core that ARM designs. And it's going to be using ARM cores, and also there are some other teams working on RISC-V accelerators for it. And here you can see how big this consortium that includes not only HPC players, but also automotive. And that's because the same technology it's meant to be exploited not only in the HPC space, but also in the automotive space. You can see here from very PhD student kind of work, very initial early work, 9 years after, 10 years after, there is a new company in Europe that is going to build an HPC processor. I think that's a great success for one of these funded projects by the European Commission. In parallel with these efforts in the Mont-Blanc project, there have been also some partners that they have been working on ARM-based processors for servers. And here are some examples that went through all these years. Early efforts were done by Calxeda. I would say that one wasn't very successful. Then AMD created the Opteron A1100 with some already 64-bit processors from ARM. And then Cavium has created the Thunder X line of processors, in which the first one was having 48 cores in 2015, the Thunder X2, 32 cores, much more powerful cores in this case than these 48. So overall, much better performance in this case. And very recently, Cavium, which is now Marvell, that was acquired by Marvell, has announced the Thunder X3 processor with up to 96 cores. In terms of success of these processors for HPC, I would say that the Thunder X2 was the first one that has been used in large deployments. And here are some examples. I would say the largest deployment of the Thunder X2 is the Vanguard Astra system in Sandia National Laboratories. And this system is built by HPE, and it goes up to 145,000 cores. So it's a petascale system with 2.3 petaflops in total. It was delivered in 2018, and they have a paper with a little bit of the challenges and lessons learned from deploying the first petascale ARM supercomputer that is going to be presented in SC20 in a month from now. But it's already available online, so if you look up for this title, you will find it there. Very good paper. Other efforts in the UK, the University of Bristol also deployed a system with Thunder X2 processors. This was a smaller system with 10,000 cores in this case. And this wasn't by HPE, this was deployed by Cray. So second system integrator in the industry that deployed ARM-based clusters with Thunder X2. And this was also delivered in 2018. Another example, in CEA in France, Atos also deployed a cluster with Thunder X2 processors. In this case, it was a slightly bigger system, maybe twice the size of the one in Bristol. So here we have the third system integrator that used Thunder X2 processors for HPC. We had HPE, we had Cray, at that time was Cray, and Atos in France. But the biggest success in terms of using ARM technology for HPC, I would say, is from Fujitsu. And that was the deployment of the Fugaku supercomputer, which is the fastest supercomputer in the world according to the top 500 list that uses the HPL, high performance LINPACK benchmark to rank these systems. The processor in this system is called the A64FX, and it's a processor designed by Fujitsu using ARM technology. The central technology to get the performance in this processor is the scalable vector extension, which is one of the main topics that I will be talking about today. This processor has 48 cores, and then it has extra 4 cores for management. From the point of view of the application execution, you will see 48, but then everything on the OS and other management tasks will be executing those 4 cores that are specific for it. It has also high bandwidth memory that is integrated in the same package of the processor. And there is no more memory than this. So the access to the memory is easy to manage because you only have one type of memory and it's very high bandwidth. Capacity may become a little bit limited because you don't have more than what you have in the chip. But for such a large system, then you can still solve very, very large problems. This is something that, of course, was deployed 2019, but it's been something that it's been going in parallel for the last decade as well, in collaboration between ARM and Fujitsu in the last 10 years. And this is a picture from Supercomputing last year, in which we had a sake toast to celebrate this great achievement. And here you have a close-up picture of the supercomputer. I was mentioning that Fugaku is the fastest supercomputer in the world according to the top 500 list. But it's not only that. It's 2.8 times faster than the second fastest supercomputer. And it's not only for that specific workload, HPL, that is the fastest. That is a very dense compute workload. HPCG is another workload that is more of a memory-bound workload. And in that case, it's also the fastest supercomputer in the world, almost 5 times faster than the second fastest, which is the Summit supercomputer in the US. HPL AI, this is a version for artificial intelligence that uses like lower precision arithmetic, 2.6 times faster than the second. And also in the Graph 500, which is another list that uses the Graph 500 benchmark, that is a little bit more network bound. Again, fastest supercomputer in the world, 3 times faster than the second. So great, great achievement, and we're very proud of it. And you can actually get your own A64FX system because there are already some system integrators that sell those. One is, of course, Fujitsu, that provides the FX1000 and the FX700 systems. The FX1000 is a whole rack with 1.3 petaflops. It has 384 nodes in one rack. And then the FX700 is one blade with, I think it's 2 of these nodes. HPE has the Apollo 80, which also uses these Fujitsu A64FX processors, and it sells the individual blades with 2 of them in this system. So you can get your own A64FX today if you like. So that was the history from how we went from toy clusters in Barcelona, PhD students working on them, many partners joining the movement, both in the server space and system integrators in HPC, growing the partnership in HPC all the way to the fastest supercomputer in the world, not only in one metric, but in most of the rankings that are used nowadays. And I think this is very important, how there are all these companies coming together is because of the uniqueness of how ARM works. And that I mentioned the word ecosystem multiple times, but I want to explain a little bit how ARM works for you to understand what that means. So ARM is a company that doesn't build processors. It doesn't. We design the architecture, we design cores, we design network on chip, we design multiple components that can be integrated in a processor, and we license those to semiconductor partners that they go and physically implement a processor with those parts. And then, of course, then we get like some license fee from that, and then that partner is gonna create those chips, and those are gonna be sold. And for each one of the chips, ARM also receives like a tiny royalty from it, and then some OEM customer will go ahead and create some computing systems with those processors. And ARM is involved in all these steps, and we provide also software support and work with the OEM customers that create the computing systems to support them in multiple levels from the business side, but also from the software support and, of course, training, documentation, and so on. In terms of HPC and servers, ARM has this Neoverse brand. That Neoverse covers everything that has to do with high-end computing. And we have a roadmap that we are looking at 30% faster processors in each generation. And we also have the ARM architecture in case somebody wants not to use our cores, but they want to create their own cores, just implementing the ARM architecture. And those are Fujitsu and Marvell with the Thunder X2 before are examples of this. They created their own cores. That implemented the ARM architecture. Fujitsu, as I said before, also Cyper is an example in which they will be using some of our cores, and then we have others like Nubia and Ampere as well. I will be showing Ampere's example later too. We have a certification. Standards are very important. So all these different designs have the same features that then you can have software, OSs, and stacks that are compliant and easy to deploy in all these systems. And that goes, of course, for compilers and device drivers and performance tools as well. Some of them actually provided by ARM too. As part of this ecosystem of partners, so ARM provides architecture, provides IP components, cores, interconnects, and so on. We have partners that implement them. We also have a group of users that is called the AHUG. And now that's, there is a board that is external to ARM. Here are some of the people that integrate that board. And this started with some effort from ARM, specifically going to the supercomputing conferences and bring together all the partnership in HPC. Now it's something that is not even driven by ARM, but driven by the community itself, which I think we think it's great. The ARM Neoverse brand is something that I mentioned before. It was created in 2018, and there have been multiple partners announcing software support, announcing new processors. Some of the examples that I'm showing here was like NVIDIA support for ARM processors for their GPUs. Then Amazon, AWS have their own processors that they use in their cloud, and Ampere with their 80 cores, and Cyper, which is the company that is implementing the European processor that is going to use Zeus core, which is designed by ARM for the European processor. And of course, the Fujitsu Fugaku supercomputer. Couple of examples that are, I think, worth highlighting. The Graviton 2 is designed by AWS. They use these Neoverse N1 cores that are designed by ARM, and also the coherent mesh network. And they put together this 64-core system that has these tiles with 2 cores in last level cache and so on. And the amount of core of these Graviton 2 processors that are in the AWS cloud is growing and growing. And there are even multiple types of instances that you can use. How these processors compare to the latest generation that they have from other companies, like, for example, the AMD EPYC 1 M5 instances and the Xeon Platinum M5 instances. They are shown here in green and in blue. And the orange ones are for the different instances using the Graviton 2 processor that uses all this ARM technology. And this is performance for Spec Int 06, Spec FP 06, and then 17. Much better performance for the cost that you invest in these instances. Many success stories of people porting their services to these processors, showing that the performance per dollar that they get gives them massive cost savings, and they get very good performance. And there have been also some blogs out there, I don't have the references here, of deployments of HPC applications in the AWS cloud running in Graviton 2, also showing very, very good benefits there. Another important player is the Ampere. Ampere has the Altra family of processors. They created this 80-core processor that implements the ARM architecture. And they have a good roadmap ahead. And they already announced not only the 80 cores system that is already available in multiple clouds, including Oracle Cloud. You can already be using these processors in Oracle Cloud, and I think it's also available in Packet. But they also announced for 2021 the availability for the Ultra Max, which will have 128 cores in one of these processors. Already with Ultra, they are showing good advantage over the Xeon Platinum and from Intel and the AMD EPYC. This is the Rome chip in the spec rate 2017 benchmark suite. So let's deep down a little bit in what are these technologies that ARM provides for partners to design these processors. And especially what are those that are available for in the context of HPC and of course as well in server. But I'm going to be focusing in HPC right now. Very recent, just I believe it was less than 4 weeks ago, there was the announcement of the ARM Neoverse V1 and the ARM Neoverse M2 cores that our partners can implement their processors with. Here is a roadmap of what was available. This N1 core series is what AWS implemented the Graviton 2 with. So it uses these N1 processors. And V1 is what will be available for partners to build future systems. And this V series is targeted to very high single-thread performance. This is looking at 50% higher performance than N1. And then N2 is the follow-on from N1 that also has like a 40% higher single-thread performance uplift. And the target for this line is to have the highest compute density in terms of performance per rack, and in the way that you can also fit a lot of these cores in each one of these systems. The V1, which is the code name was Zeus, is the one that Cyperl, as I mentioned before, is using for the European processor. Is this V1 core that it will be using for implementing it. And nice thing about it is that all these future cores are implementing the scalable vector extension SVE. In terms of what was available up up to until the V1 core and before Fujitsu implemented SVE in terms of SIMD or vector compute was this technology called Neon. And Neon has been very successful in the mobile space, in the signal processing and crypto and so on. This was a vector extension that used fixed width. So each one of the units was computing on 128-bit vectors. And the way that it works is that you have this vector with these 128 bits. And when we are talking about SIMD or talking about vector compute, the thing is that one instruction is not going to be executing on one value, but it's going to be executing in multiple values at the same time with one single instruction. So if we look at this floating point addition here, in this 128-bit register, we're going to have 4 32-bit floating point values in which you're going to be operating. So you're going to be taking these two registers, doing the addition, and then storing them in the destination register. So with just one instruction, you can go ahead and perform these 4 operations at the same time. But that was, of course, not very attractive for HPC. So the scalable vector extension was invented. This is an effort that I'm very proud to say started in ARM research and was later productized and now being deployed and now part, of course, of the fastest supercomputer in the world. It's, of course, based on 64-bit execution for the ARM v8 architecture. And I want to highlight the word scalable here. Why we call it scalable? Before I was mentioning that Neon was operating in 128-bit registers. And there are some other instruction sets, vector instruction sets or SIMD instruction sets by Intel and others that they have fixed size. They may say, okay, I have this instruction set that operates in 256 bits or in 512 bits. And that's mandated by how that specific instruction operates. In SVE, instructions operate on vectors of any length. There is no specific length in which this vector operates. The length that is implemented in hardware is a choice for the partner to implement. And that makes sense because we may have partners that want to implement SVE for a specific use case, maybe HPC, in which they may want like wider vectors. And there may be some other cases in which they may want to implement it, I don't know, maybe for a cell phone in which they may want shorter vectors for some other reasons. So at the end, you can implement this in vectors from 128 to 2048 bit width in increments of 128. So every 128 multiple in this range is a valid vector length for an SVE implementation. And that allows something that I think is attractive, which is this vector length agnostic programming. You can program from it being independent of the length, and then the same code will run in machines that are implementing different vector lengths. SVE also added some features that help with auto vectorization, and I will be showing some of them later. And it's one thing that I wanted to highlight as well is SVE was initially designed for HPC, not media processing, not image processing, not other types of specific use cases for which Neon was optimized and targeting. SVE was targeted for HPC and also added some features for machine learning that I will be touching a little bit on those later. What is this vector length agnostic programming model? Nice thing about it is that you write the code once, you compile it once, and then that same binary that actually you can vectorize over more loops than Neon will run in different machines that may implement different vector lengths. This is something that you cannot say from other architectures in which if you coded for a specific vector length, like for instruction ISA that was a 256-bit, and then you get your new shiny processor with 512, you cannot just exploit that 512-bit. You have to recode your application to make use of the wider length. In SVE, that's not the case. Same binary will go and exploit the whole length in the different implementations. Those implementations go from 128 all the way to 2048, as I said before. And one thing that makes this possible, and one thing that makes this also attractive from the point of view of implementation and programming, is that it's a whole instruction set that is predicated. And I will be showing what predicated means later. But the nice thing is that you will have these predicate registers to specify how you want to operate in these data elements. Just to show a little bit more graphically how this works, you will have a hardware that has a specific vector length, like for example 512 in the Fugaku supercomputer. But in software, you don't have a specific length. It can be any length. And then it will be in your specific execution in your hardware, for example, a 512-bit core or a 256-bit core, in which that same instruction in that binary will be operating in more or less elements, and therefore will have to do more or less iterations in the specific loop that is using these vector instructions. And there are a set of features in SVE that makes it also a better target for auto-vectorization. Some of those features, I'm going to be just briefly touching on them. One is gather, load, and scatter store. This is something that wasn't available in Neon at all. This means that if you have data that is in non-contiguous places in memory, and you want to operate on those at once, you can execute one of these gather loads that is going to go to memory and bring all those pieces, put them in one register, and then perform operations on that, and then it will scatter those values back to those non-contiguous memory positions. If you don't have this capability, and the values that for which you want to vectorize, they are not contiguous in memory, then that becomes code that you cannot vectorize at all. And with this feature, now you can. Another nice capability is these horizontal reductions or horizontal operations, in which you want to not operate in the multiple lanes individually, but you want to operate across the values within one register. Let's say that you have one register with these 4 values, and you want just to add them up into one single value. There is one instruction that will do just that, with the one instruction not having to go in each one of these one by one. It will just go and do this operation and generate one scalar value out of the whole vector. Per layer predication, this is, I think, central and very, very important in SVE. That means that you will have a couple of vector registers, which are these 2 gray registers here. And then that instruction that can be an addition in this example is predicated with a predicate registers. And a predicate, what tells you is that for each one of the lanes in the vector, for each one of those values, whether you perform the operation or not. And in this case, we are showing that for the first lane and for the third lane, you perform the operation, but for the other lanes, you don't. And this is good for loops that have if statements in between, in which you may want to execute the operation, but only when the if statement is, the condition is true, for example. These predicates are also very important for the end of a loop. When you're finishing operating in that loop, sometimes you will see that the iterations are not a multiple of your vector length. And then what happens in other architectures that don't have this support is that you will have a remainder loop or a tail loop or a head loop in which you will have to perform the one by one operations for each one of the elements outside of the multiples of the vector length. And I will be showing a little example with that later. With predicates, you don't have to, because what you will do is that you will just disable the operation for the elements that go beyond the iteration range of that loop. And then there is this other feature, which is this software managed speculation. This is a feature that is useful for something like string processing. If you are operating on a loop, you know how many iterations you're going to do. But if you're operating on a string, you don't know when the string is going to finish. But you can perform this execution, the execution, by looking at where you find the final string. The problem is that you may be performing some loads beyond memory that is allocated, and then you will have a fault that is not valid, let's say, in software. You are just speculating beyond the computation that should have happened, because now you are using these vectors that operate on the multiple values. In the example of a string, it will operate on multiple characters. With this feature, you will be masking that fault. That fault that you get from accessing non-allocated memory space, you will be masking it. It returns you a predicate, and then you can do the operation using that predicate. So very useful also to cover the vectorization for codes that you don't know how many iterations or how far you can go into loading from memory with these vectors. SVE registers are the ones that hold the values in which these vector instructions operate. And those are these Z registers. There are 32 of them, and they will have a length that is the vector length that implements that processor, that are multiples of 128. And these SVE registers also hold the registers for Neon. I was mentioning before that Neon is a 128-bit instruction set, and Neon coexists with SVE in these processors. So the lower 128 bits are the ones used by Neon. The whole thing is used for SVE. And it supports a wide set of data types. Double precision, single, and half floating point elements are supported. Also, bfloat16 is supported. I will touch on that later. And all the sizes for integers from 8, 16, 32, 64. And then we have the predicate registers. These are the registers that I was saying before are used to enable or disable the execution of the instruction on each one of the lanes. How these predicate registers look like? They look like this. They will be 1 bit that predicates the operation in that one lane. And of course, you're going to be using more or less bits depending on what is your vector length, and also depending on what is your data type. If you have a 256-bit vector and you are going to operate on 64-bit elements, then you're going to use 4 bits for the predicate. But if you go to 32-bit elements, for example, then you will be using 8 bits instead. Apart from these predicates, of course, the generation of flags, like for conditionals and so on, it's also dependent on these predicates. So I think that the main message here is that predicates are not an afterthought, like in some other architecture that they added predicates afterwards. Is something that it's fundamental and it's central to SVE. So let me show you like a visual example of how the SVE would compute against some other types of traditional instructions. When you're operating with scalar instructions, then you're doing maybe one addition only in one element, one value. And let's say that you have to do 10 iterations over this 8-byte, 64-bit registers. So you're going to be operating on 10 values. Then you would be executing 10 instructions, and each one of these shot glasses is one of those scalar instructions. In something that like Neon, that is 128-bit and is fixed length to 128-bit vector length, then you can operate not only in one value at a time, but in two values at a time. And then you will be operating in these 16-byte registers instead of the 8-byte. And then you will, these two guys will be operated in one instruction, these two ones in one instruction. So you will be executing only 4 iterations instead of 10. But then the 10 iterations are not a multiple of the two. Sorry, they are not a multiple of the whole iterations that you have here. So then you will need these additional 2 scalar instructions in that case. With SVE, we are operating. This is an example with a 256-bit register and vector length, and using predicates. In this case, it will be able to do 4 at a time. So it will be covering all this with only 2 iterations, but then you will have to do 1 extra iteration in the loop, but you want only to operate on 2 of those elements, not in the whole thing. So you will be predicating that you operate in 2 of them, but not in the 2 remaining ones. And this is the whole concept of how this works. The thing is, in this case, the size of the glass is fixed. But what about SVE? In this case, it's something that it can go, as I said before, up to 2048. Nice thing about it is that if you want to operate in smaller size, let's say that you have a 512-bit implementation, but you want to execute with 256 or you want to execute with 128, that's something that you can set from the OS and execute your code with that length if for some reason your code is optimized for it. So that's also a nice thing about SVE, is that you can configure the vector length to shorter sizes, and the instructions will execute just with half or with that smaller vector length. Since the announcement of SVE in 2016 in the Hot Chips conference, we've been working with the open source community to provide SVE support in libraries and the whole compiler set. And there was initial support in all these versions of these compilers, GCC, LLVM, of course, support for emulation as well if you want to emulate SVE in that case, debuggers support as well. And this was the first version that had some support, but that support has been improving. And I can give you, like, for example, in GCC 8, there was some auto-vectorization capabilities for SVE, but those were just basic. It was improved in GCC 9, and in GCC 10, I can say we have full auto-vectorization support that covers a lot of the loops there. And we're upstreaming also support for in LLVM and the Linux kernel for SVE as well. ARM also has its own compiler, and I will be talking briefly about it later, and that's built on top of LLVM. And many of the features that we have in the commercial compiler that's supported commercially, we also upstream to LLVM as well, apart from all the other open source projects that we support. So just a quick recap on SVE. It's a central technology for SVE, was initially thought with all the capabilities that are attractive for SVE, and it's today the technology that powers the fastest supercomputer in the world. You write the code once, you have the binary ones, and you can execute it in different implementations with different vector lengths with those predicates that I mentioned. And you can go from smallest implementation, 128-bit, all the way to 2048 bits. Something that can be also adjusted by the OS. And nice thing about it is that it also allows to vectorize a wider range of codes. And we have been uploading all the support for in open source and compilers, libraries, debuggers, and OS support in open source. And we also have a set of commercial tools that I will talk about later. And this is SVE. What comes next? What comes after SVE? First thing I want to talk about is in all this time, the importance of machine learning has been growing more and more. And since we announced in 2016, SVE, it's been growing at a very, very fast pace. One of the important additions in the world of machine learning is this new data type called brain float 16, or BF16 for short. And it's something that lies in between FP16, the IEEE format that has 16 bits for the exponent and the fraction of the floating point value, and the FP32. So yeah, just to show it as a basic idea, is the exponent is going to determine the range of values that you can encode with that data type, and the fraction is going to be more or less precise with that within that range. If you go to this FP16, the exponent is smaller. You have only 5 bits, and then in that case, your range of values is smaller. In FP32, your range of values is larger. Key insight here is that for machine learning, many times being imprecise is not a bad thing. It's okay. The algorithms are going to converge at some point, but if you can operate into half of the bits, you are effectively doubling your throughput. So why not having a data type that is less precise, but covers the same range of FP32, and that is going to have half of the computational requirements, which means it's potentially going to run twice as fast as a FP32 without having to lose the range that you would lose if you go to FP16. And this is something that is added into some SVE and in Neon as well. And there are multiple instructions that support this. And I'm going to talk about specifically about this matrix multiply instruction that is also a new addition to SVE. The support for bfloat16 is something that is already present in the ARM NN, which is a library for accelerating neural network in the HPC space. And then we have also the compute libraries, which are more of a specific deep learning, maybe for lower end devices. And BF16 and vectorization with all these instructions is already supported in those libraries that are optimized for specific implementations. Another addition is to have higher throughput is the matrix multiply instruction. But before I talk about matrix multiply instruction, I want to talk about what was available before this matrix multiply instruction. And that type of operation in matrix multiply in HPC or machine learning codes was done either through this multiply and add instruction. What it does is that you have, in this case, I'm showing 2 vector registers with 4 elements each. The width is 128 and each one is 32-bit wide. And then this multiply and add, what it would do is to multiply the 2 elements in one lane and then accumulate the result into the destination register. And that would do it for each one of the lanes in the vector. This was supported for a range of types in different sizes of integers, bfloat16, floating point, and also complex complex numbers as well. Available for both Neon and SVE through these instructions. Then we have the dot product. This is for smaller data types like int8 and int16 and bflog16 as well. Available in both Neon and SVE, same instructions. And in this case, I'm showing an example with 8 of these 8-bit. Sorry, in this case, it's int16 elements. And in this case, you would have a multiplication for each one of the pairwise elements in each one of these lanes. And then you would accumulate them in groups of 4. So you would take the results of these multiplications and you would accumulate them into one value that then you go ahead and accumulate into one element in the destination register. To be able to do this multiplies and accumulation in a way that's precise, the data is extended in this case from 16 to 64-bit elements. And in the case of 8, it's extended to 32. In this case, we are seeing that for each one of the values, we perform 2 operations, one multiply and one addition. Same thing here. For each one of these guys, you will have one multiply and one addition. If you count all these guys here, those are 8 operations on 4 values. And here it comes the matrix multiply instruction. This matrix multiply instruction is available for Neon, for int8 and bflog16, and in SVE in those data types, and also for floating point. So in the case of SVE, it has support also for these matrix multiplies for HPC as well. The way that it works is that instead of working with vectors, you're going to work with 2x2 matrices. And here I'm showing these 4 values that are going to be stored in one register, and they are going to represent a 2x2 matrix. Same for this other matrix, and then you're going to be multiplying them, and the accumulation is going to be happening in a destination register that again represents a 2x2 matrix. In this case, it's a typical matrix multiply operation. For each one of these destination elements, you're going to multiply the row and the column, and you're going to perform the accumulation in this case. Nice thing about that is that you can replicate the inputs to perform double the amount of operations per element. And in this case, you will replicate these 2 guys here, and you will take these 2, and then you will perform this operation. But the same 2 elements, you're going to go ahead and multiply them by these other 2 elements. And then for each 2 lanes, you're going to perform double the amount of multiply and add operations, which means that you are effectively doubling the throughput. Now you're performing 4 operations per element. And in the case of prior to matrix multiply instructions for a vector length of 256, you would perform each operations every cycle, or for 5, 12, 16. Now with this instruction, you will perform in 16 or 32 operations in one given cycle. So twice the compute throughput for machine learning and HPC with this instruction. A bunch of new other instructions came also with the announcement of SVE2. This SVE2 includes a wide range of new instructions, again with the same basis of being vector length agnostic, predicate centric, and so on. And the idea is to widen the range of applications of SVE beyond HPC and server and machine learning. Now all these new instructions in SVE2 are for DSP, computer vision, as you can see here, cryptography, networking, genomics, and so on. And that's something that provides value for these vector extensions beyond the HPC market. Here are a list of what's new in SVE2. And of course, you can read them by yourselves. I just want to highlight a couple of them. So one is the addition of these non-temporal gather scatter instructions that are good for HPC. So these are gather and scatters that you know that you're going to be using once, and so you don't need to cache them. And then there is also a way to accelerate histograms with these new instructions, and that has also some value in HPC, and also accelerates sorting algorithms and so on. So I'm going to touch briefly of what are the typical ways to use SVE. I would say that there are multiple ways to use SVE, and that depends on what is the level of effort, the portability, and how much you want to get out of it. The easiest way is to just use libraries that are optimized using SVE. So you just load your library and you call that library. And one example would be the BLAST library that implements linear algebra operations, like, for example, matrix multiply or matrix vector and so on. Those are implemented and optimized for the multiple processors out there that implement SVE. You can also take your compiler and have it vectorized, and for that you will just have to use this flag, and it will vectorize the codes for you. If you want to go beyond that, you can use pragmas, and in that case, it's like using a hammer. It's like telling the compiler, I'm telling you that this loop, you can go ahead and vectorize it, even if you find some conditions that you think you cannot, go ahead, do it. Then next level of, let's say, effort is using intrinsics. These are some specific C mnemonics and C instructions that you can use, that then they map to a specific SVE instructions, and then the compiler will do it for you. And the last one is to just hand code in assembly. Just to show something that it was added recently to the ARM compiler for Linux are these vectorization reports. So if you use these flags in the compiler with a line like this, it will tell you whether that loop was vectorized and whether it was also unrolled and so on, whether it was inlined, and it's giving you all this nice visualization of the optimization that it could perform. In terms of tools, I talked about the compiler and the performance libraries. Those are very important and very good in the context of HPC, but it's very important also to have some performance analysis tools. And for that, we have the ARM Forge that includes these tools and the performance reports. In terms of libraries, I mentioned before BLAST, which are these linear algebra libraries. It has all these routines that they are optimized, and not only BLAST, also FFTW, LAPACK, and also some support for sparse matrices as well, with different sparse representations. What else here? I think I just want to say that these are optimized for specific implementations, like, for example, Fugaku, for example, ThunderX2, and for example, Graviton 2. I think that we're working on that too. And that's also validated by the NACC test suite. And that's something that is, you can use this library both if you compile with the ARM compiler or if you use open source compiler like GCC, for example. It provides already some good performance improvement. These are some HPC workloads. This is execution time, so lower is better. This is if you compile with GCC, the performance is in gray. If you compile with the ARM compiler, it will give you this bar. If you, on top of that, add the utilization of the optimized libraries that implement this exponential and power and sinus, cosinus, etc., it gives you further improvements in performance. As part of ARM Forge, there are two parts to it. One is the debugger, which is DDT. The idea is that it's scaled to hundreds of thousands of nodes, and you can debug these parallel applications. And the profiler that it will tell you what are the parts of your code that are being executed the most, and how you can optimize for it, how you are spending your time in MPI or OpenMP, and multiple metrics in terms of CPU utilization, memory utilization, and so on. The typical type of information that you will get from your profilers, but to very large scale and designed to go to hundreds of thousands, of course. In terms of specific now lower level specific analysis tools, there is the ARM Streamline Performance Analyzer that I'm showing here. It provides performance counters and so on. For ThunderX2, there is this liquid that I think is pretty good. And one that actually I was very surprised is the one from Fujitsu. So if you get the Fujitsu A64FX with the Fujitsu tools, you will have this FAPP profiler that provides a very, very detailed report on the utilization of the multiple components in your system. That one is pretty impressive. So I think I have a few more minutes, and I'm gonna touch on what comes in the future. I am, of course, in research. So I'm sorry that I showed some marketing slides, but you cannot hold me accountable for those. I can talk a little bit more about what we are doing in research, looking at future systems and what is the basis for it. The main motivation for us and how we are basing our research for future HPC systems post exascale, and also technology that can be also valuable for data center and for the cloud, in which we are seeing more and more HPC computing happening, is that it's all about cost, and it's all about scaling. One of the metrics that is very important in these large deployments is cost of ownership. And that's a metric that many times is trying to optimize this cores per rack, how much compute you can pack in the least space possible. Another motivation is that the size of problems in data science and machine learning, and also in HPC that we are seeing, is growing at a very fast rate. And that's something that is very easily motivated with the example that I showed at the beginning with the array of things. These are sensors that are gathering massive amounts of data. This was also highlighted by Pedro Alberto at the beginning. And the amount of the problems, the size of the problems that we will have to solve becomes bigger and bigger. So you need to scale your system to be able to cope with the larger and larger problems. So we think it's all about high compute density. So you can have, for lower cost, larger systems. And it's very important that that compute density becomes as integrating more and more components within the same processor, so you can build very fat nodes. When you build those very fat nodes, then you will have less glue per core, so you are going to have less overhead in terms of the rest of the system, networking, and so on, that you need for each one of your pieces of compute. And very important also for energy efficiency is the data movement. You want to use the least amount of energy per bit that you need to move of data. And in that case, if your compute is packed more densely, of course, the cost of that data movement is gonna be slower. Just want to mention why cost is so important. GPT-3 is one of the biggest, probably the biggest still, largest neural network model that was announced by OpenAI. I think it was earlier this year. 175 billion parameters. Training this network costs $5 million. So you're going to train this network, you're going to spend 355 GPU years, and it's going to cost you $5 million. So we need to make the scale of our systems in a very cost-conscious way to provide the highest compute density to the lowest cost. And the main motivation for us to look into this research is there is a shift in scaling processing. Moore's law is something that I'm sure you all are aware of. We have been able to put more compute in our processors because the transistors were getting smaller, so we can pack more and more cores, more and more memory, more and more cache. But that's slowing down, and that's going to be stopping soon. So in the post-Moore era, in which you cannot just grow your processors larger because that provides like a much higher cost, we see the scaling through advanced chip packaging and creating multi-chip processors. And that's something that we are already seeing out there, but for us, I think it's going to be something that's going to be picking up very, very soon. I see some questions in the chat. Yes, I'm just finishing. I'm just in my last 2 slides. So we are looking at not scaling these systems not only by making chips bigger, by putting multiple of these chips in the 2 dimensions side by side, or on 3D, one on top of each other. And in that case, you have smaller chips, you will have higher yield, and it's also simpler to design and test, and the cost will be lower. And here are some data that was shown by AMD this year at ISSCC 2020, in which they were comparing their chip that has multiple dies, that is the blue one, to a hypothetical implementation in which they would have put it in one single chip. The cost reduction is massive, and they could go to a size 64 cores that is not even possible by doing it just in one chip. So we are focusing our research on scaling these processors to thousands of cores, leveraging this 2.5D and 3D integration. So we can have that higher performance and lower cost by scaling horizontally with 2.5D. And then not only higher performance and higher efficiency, but also higher connectivity and lower energy cost for data movement by going 3D. And by having those multiple chips, we can also have maybe some parts of the system like I/O and so on in older technology nodes and compute in a newer technology node that gives also a cost advantage. And that way, with these multi-chip systems, we can compose smaller processors maybe for automotive space and larger ones for HPC. So just to wrap up, I went through how important is HPC for society through the global goals, the Mont-Blanc project, how we went from the initial prototype, Mont-Blanc prototype, multiple partners joining Bristol, Sandia, RIKEN, all the way to the fastest supercomputer in the world. We also have some impressive processors that are coming out through AWS and Ampere for servers as well. We provide architecture, cores, interconnect IP, standards, software, and our partners implementing systems with that, all the way to SVE as well. That is, as I said, in Fugaku. We already have a roadmap post SVE with those tools that I showed, and we have some research looking into what will come for HPC systems post exascale, looking at scaling compute density very, very aggressively. This is the end of my talk, and now I will be happy to take any questions. Here you have some of my data to contact me, follow me, connect, and you have the arm.com/HPC webpage in which you can get more information there. So, thank you, and now I will be looking at the chat to answer any questions you may have.
Yeah. Yes. Let me just thank you very much, Alejandro. I think it was a very, very nice and complete presentation about the ARM architecture and its applications. So if you have any questions, please put them in the Q&A section, as I told you first. So otherwise, I will have my own questions, but let's wait. I think up to now we don't have any questions, so I take the opportunity to have some of my own. If you, yeah. So I think it was very interesting. Really, start my video. Yes. Okay. Let me. Yeah. So yeah, let me show my face. Several questions. One of the things. Let me start with this one. Of course, one of the goals and the interest of the ARM architecture was to have big savings in energy costs, of course. You didn't mention too much of it, but I think that is a central thing, right? Besides all the, sorry, the architectural questions and of course, in the relevance that you mentioned, but I think this energy saving, also reducing the cost of ownership, as you mentioned, through the energy savings was very important, I think. Is working?
Yes, yes, I can hear you.
Then yeah, sorry, Dan is writing something, is maybe because a panelist, I don't know. But
well, I can see the question.
Yeah. I'm not sure it's easy to type a question, but
yes, sorry.
type chat.
I opted to make it alive, if you make, but okay, this is just one of the things. Other questions related to the, sorry, to all that architecture and so of course ARM licenses technology, so allows several vendors to have their own chips, and you mentioned several of them. Is there any common? I mean, if you develop tools for any particular chip, is it common to the other ones? And I mentioned this because, as you know, software stack is very important. And when I was looking to your biography and all the publications, I noticed that you were involved at this cell processor research at the very beginning. I think the BSc had a cell machine as well, and I know that this was not very successful base. One of the things was very hard to port the codes to this architecture. So I guess ARM is taking care of that, but how can we know, or how can be some software development or codes or any tools be available to the whole range of ARM CPUs, if it is, or just they are particular to a certain kind of CPU? Okay, that's my question. Thank you.
Yeah, I can answer that, and it's a very good question in the context of ARM, because of course we come from a expertise on the lower end of devices, microcontrollers and cell phones, tablets, and so on, in which you can say it's pretty much custom designs, right? So you're gonna build your specific device, and you're gonna build the whole motherboard, the whole integration of the device specific for that one smartphone, for example, or for that, I don't know, processor that is going to go into a washing machine or a microwave or whatever. And when we went into the HPC and server, something that was lacking, very important in these markets, was the existence of standards. How you're going to boot, how you're going to connect devices, what the drivers can assume, and so on. And early implementations, you had to go and always change something, always change booting code, or changing some specific support for some specific interface that you may have in that particular processor implementation. As you said, there are many of them. And one effort that has been very, very important, also supported by people in the community, not only by ARM, also by people in Red Hat. John Masters is one of the people that has been very vocal about it, is to establish some standards. And ARM has created the SVE ISA, which is the server-based standard architecture, that sets a set of rules that you need to comply with to implement in your hardware. So software that is compatible with those rules will run with no problems in that hardware. And now, very recently, we have introduced this server-ready certification, which is a testing tool set and some validation suite in which you can run it and verify that you are compliant with that. And then any OS, any libraries, any drivers that are compliant, that are server ready, will just go and run into those multiple implementations. So I guess my answer is it's all about standards in the way you can assume this will work with any OS that you can download there that will have support for it. That's of course for support. In terms of optimization, then yes, you will have to optimize for different processors, but that happens with any different processors also from other manufacturers that they have different microarchitectures. I want to just highlight, for example, the fact that we are having not only the support from Fujitsu with their whole software stack, they have their compiler, optimized libraries, MPI libraries, and so on. The same for Cray HPE, but also we are supporting the OpenHPC effort, in which there is a set of open source OS libraries, programming models, and so on that are fully supported and that are tested across this range of processors as well. So we make sure that they work. So I would say standards, effort from vendors for their particular implementations, and then open HPC effort. I think it has been also very important.
Okay, thank you. I must one thing that I forgot to mention, but this session has been recorded, so everything will be available later on. Sorry, but I think Dan wanted to ask some questions, so I think there is no questions in Q&A. So I think if Dan wants to ask you something,
sure, I can ask a quick one here. I know we just have a couple of minutes left, but so wonderful talk, Alejandro. So you probably can't talk about ARM being acquired by NVIDIA because the deal is still pending, at least from the ARM perspective. But with that out in the public media, can you talk about what you think it might mean for NVIDIA's future directions that they've acquired ARM, in your opinion? So.
What will you're saying about NVIDIA? So how that would affect NVIDIA, the ARM acquisition?
Yeah, they've obviously done this for some particular reasons. I have my own speculation, but what do you think will happen? How do you think it'll change NVIDIA going forward?
I mean, what I can say, it's what I know, which is the same that you know, because it's been publicly mentioned multiple times, also with their stakeholder meetings internally at ARM, internally at NVIDIA, but also this week we had the NVIDIA GTC conference and the ARM Dev Summit conference, in which NVIDIA CEO Jensen Huang was there. And the main thing that they want to change and the main thing that they want to leverage is the ARM ecosystem of the ARM partnership. And they are looking at even not only keep providing that the same range of IP that ARM provides today to all the partners in the same way with the same roadmaps that we have and everything, but enrich the offer in the IP portfolio for the ARM partnership with NVIDIA GPU IP. And that's something that they have been saying publicly as well. And I think that's going to be the main change, is that they want to keep both more of the vertical and the horizontal. I think ARM is probably the most horizontal business in the whole industry. And they want to keep that because they see a lot of value into bringing all those partners and keep them engaged for the current ARM technology, but also adding on top of that the everything that NVIDIA is designing in-house and implementing themselves, but also providing some of that IP for partners to implement. I think that's going to be the main change for the industry. We will see, or I see more partners implementing, for example, using NVIDIA's GPU IP, which is something that you don't see today.
Thank you.
Does that answer the question more or less?
Mm-hmm.
Okay.
Okay. So I think there is no other questions. Nobody has. Yes. So in Q&A, I guess. So if everybody agrees, I think you take at least according to schedule, there should be now a break. So but please don't go away, because Dan usually gives a very interesting and very informative talk. So so according to the schedule, we'll reconvene at about 5 to 4, so 3:55. There is a break now. So if I'm not those, I think that's what I was told. So yeah, so in principle, if there is no other break, no other question, then we now have the break until 5 to 4. Locally, sorry, it's 5 to 10 in Austin. Okay, thank you. Hello, welcome back. Second part of this session. I suppose everybody's there. Okay, thank you. So I think we can begin second part. I take the opportunity again to thank Alejandro Rico by the very interesting and nice talk he just gave us. And now is the time for Dan Stanzione. He's a very well-known personality of the HPC community, but then anyway, I'll give some words. So Dan is currently the executive director of the Texas Advanced Computing Center. He has been a PI of several HPC NSF projects, leading to some of the biggest supercomputers in the US and in the world. He has a lot of experience, big history working with TACC. On some personal notes, I've going to supercomputing conferences, both in the supercomputing in the US and the ISC in Europe. I've the privilege of attending some workshops, or sometimes just feathers, so just small sessions in which it was discussed some HPC technologies and features. And it was always interesting to listen to Dan, because he has a very user-focused approach to HPC, which I think is very, from the point of view of users and people really use HPC, is very interesting. And another personal note, I just want to recall a visit that we had pleasure to welcome him in Coimbra here in the 2008 for the first TACC Summer Institute, that the first edition of the UT Austin Portugal partnership, and it was very nice to have him, and of course all the team from TACC here. So without further ado, then I'll ask Dan to start his presentation. Thank you.
Thank you very much, Pedro. And before I get started, it says I can't share my video because the host has stopped it. So if I could ask whoever's doing support to re-enable video sharing. I think I can share the slides, but not the picture of me, which might be the ideal scenario. But there we go. Thank you. So Pedro, thank you very much for the very kind introduction and the invitation to speak today. That trip in 2008 that you mentioned to Coimbra was my first trip to Portugal, but since then, in the last 12 years, I've been fortunate enough to come back many times. And we are really excited about our continued collaboration through the UT Austin Portugal program. And as many of you know, the current machine in Minho, which will soon be replaced by a new one, but came from machines from TACC that is now part of the Minho Advanced Computing Center. So we've sent a bunch of computers to Portugal, but you have sent many wonderful students back to spend time with us doing research, who are wonderful and talented people. So I think we're winning the collaboration so far. It's been exciting, and I'm so sorry we can't be there in person today or welcome you to Austin, but it's just not the ideal time for that. I'll talk a little bit about some of the reasons why as we go through. So what I wanted to do today, since we have a lot of time, and I will admit that as Alejandro gave his great talk earlier today, I was rejiggering slides and pulling some out and putting some new ones in as he spoke. So he gave you a lot of the sort of background about HPC in general and some of the fields where it's used, and I'll still do a little of that. So I want to start with sort of the state of the art in HPC, and doing that by giving a little background about the Texas Advanced Computing Center, where I am. And then to talk about how things are changing. The title for this session was Emerging Trends in HPC. I think they're changing really for three reasons. One is the technology, which Alejandro covered part of, and I'd like to dive into again. One is the state of computational science today and how it's changing, and that's driving us to change HPC. And then there's some broader, just sort of cultural, social things that I'm calling societal drivers that are also forcing us to change. And so then we'll talk a little about how things are evolving and how I think they might evolve even further in some of the experiments we're doing in that direction. So let's just start with a little background. I know many of you, just looking at the attendees list, know about TACC, but if you have not had the chance to visit us or hear from us on our trips to Portugal, we are about 185 people focused in deploying and operating HPC systems and the associated software and capabilities for computational science. We operate about 12 megawatts of data centers. We have 15 production platforms, including the two largest academic supercomputers in the United States and the largest one in the world. The second largest one in the US and number 22 in the world is Stampede 2, which is right behind me. If you're looking at my little thumbnail video here, it's not really right behind me, but you know, it's the age of Zoom. And the other one is Frontera that I'll talk a little more about. About to show you, which is was the number 5 machine in the world with the debut of Fugaku and that Alejandro mentioned, and a couple of other machines. We've dropped to number 8, but we overall put out about 9 billion compute hours a year and store 100 petabytes of data for about 4,000 significant science projects to about 50,000 users around the world who make use of our systems. And I'll give a few examples of that. But since you know, in addition to me not getting to come to Portugal, none of you get to come to Austin lately. So I thought I'd just take 45 seconds or so and showed you what you'd see if we were holding this meeting in Austin. You'd come into the Advanced Computing building here, where we used to spend all of our days and now spend some of them in the age of COVID. And you'd wander back to the data center, and in the front, you would see Stampede 2, our large machine that covers many, many different broad science missions. And then you'd work your way to the back few rows of the data center right here, where you would see Frontera. Those are 58,000 watt racks that are about 8 feet tall. And that serves the deeper missions, less missions, more time to each one. 45 miles of fiber cabling that go into that machine across the top there. It's very dense racks, as Alejandro talked about. That's the 50 petabytes or so of storage and 3 petabytes of flash storage sitting on top. The GPU component of Frontera actually sits floating in mineral oil there, and that's how we cool it. The main processors we're cooling with direct water cooling and chiller doors, which means we store about 1 million gallons of water out back, about 4 million liters of water out back, and have extensive infrastructure to actually cool this. And cooling is a big challenge that I won't spend too much time on today. But that is Frontera itself. Again, was number 5 in the world when it debuted. It's a little over a year old now, about 16 months old. It's dropped down to number 8, but it's supported by the National Science Foundation, and one that we've done just some amazing work on many things, including COVID this year, that I'll get to in a moment. And so Alejandro did a really nice job of setting the stage, but let me just say that our history in sort of computational science and engineering and in the implementation of that in high performance computing started in the fact that we can mathematically model so many the physical phenomena in the universe. And so from sort of the 1940s till the mid 2000s, I would say, most of HPC was about things that we could model largely around differential equations and build, high precision floating point models of, and there's, again, so many things in the universe that we could model that way. And this is still sort of the core of what we do, but it is something that has certainly expanded. And one of the big trends in the last 15 years of HPC is the fact that we have so much easy to acquire and cheap to acquire digital data. And I'll talk more about this, but you can imagine omics and imaging and LiDAR, big instruments like LIGO, small instruments like Internet of Things, which has changed the set of skills that we have in our users and introduced AI into the world of HPC. And again, we'll dive a little deeper into all of this, but the gist of that is it has changed dramatically in, I would say, in the last 12 or 14 years, what our interfaces to HPC look like in about the ways people use it, in the ways that they want to demand time on the systems. And many of them are blended. So Jupyter notebooks, web interfaces, APIs. And today our efforts at TACC, we still build big hardware systems and big visualization systems, but we put probably 70% of our effort into reproducibility and data analysis and data management and building the software and tools to interface to HPC. And that's a big part of what we do. And so I like to think of what we do is really larger than HPC. It's cyber infrastructure, which is both the hardware services and the software services we need to support these sort of evolving workflows. And I think, and I'll get to what I think is happening next in workflows, but what's happened in the last decade is we've moved from just pure simulation, where we build these mathematical models largely based around differential or integral equations. And when we want to ask questions of those models, we do simulation. As data has gotten cheaper, analytics has become a big part of the HPC workload, where we're essentially asking computational questions of our experiments. And then finally, as we put this data into big corpuses of data that we can cross-reference across, we've essentially changed from sort of first principles-based modeling to statistical-based modeling of those, largely around deep learning. But so machine learning and AI is largely about building a computational query of our data sets. And so, we've done, in the last few years, a lot of our science and engineering has combined all three of these, and that those trends continue and accelerate. We'll get into that. So the kinds of problems we've been running, and I would be remiss not to talk about COVID-19 related problems, but just to start with something else for a change, and we'll get back to COVID. So this was a fairly recent work on tornado simulation, which will tie into a theme later, but this is Lee Orff at the University of Wisconsin, and this is a simulation that runs at a little over 200,000 cores on Frontera today, so about half the machine. It's one that is sort of GPU hostile, so it likes our machines better than it likes the DOE machines, the Department of Energy machines in the United States. And in this particular problem, it's about finding new dynamics in tornadoes. And there aren't very many tornadoes in Europe, but there's an awful lot in the middle of the United States, especially in the spring. They're fairly hard to predict. And in fact, we issue, for the tornado warnings that get issued, tell people to go in their basements or whatever else, we issue them at about, only 30% of the warnings result in a tornado. What we'd like to do is not, a higher yield. We'd like to get that to more like 80%, which doesn't mean we want more tornadoes. It means we want to issue less warnings. And what we've discovered is that adding physical resolution to the simulation lets us understand new dynamics about how they form. And so these are these sort of super high resolution models that are massive in scale, right? Many petabytes of RAM, or hundreds of terabytes of RAM being thrown at this, several gigabytes times 200,000. In this case. So give us new physical insights into what goes on. So simply by scaling up the size of the system and the problem, we can learn new things in tornadoes. Another example, and this is one of the places where we sort of cooperate with the commercial cloud, is in climate simulation. And this is the work of Ping Chang at Texas A&M with some collaborators at INCAR in Colorado. In the US, it's the National Center for Atmospheric Research, and QNLM, a university in Taiwan. And they're doing global simulations that are massive in scale, but also produce a lot of data that needs to be shared. And they take about 550 gigabytes of data, and they use the Frontera bridge to the cloud platform Azure, and publish the data there, where there's an analytics tool suite to dig into it. And another trend we're seeing is that also sort of relates to cloud type workflows, is using Frontera as an automated service, right? So here, the user is a system of software and not actually a human running jobs on Frontera. And this is using the slide is stolen from Rob Gardner. I've stolen very many slides because there's so much easier to steal from smart people than to do your own. But Rob Gardner is at the University of Chicago and Fermilab, and he has this project Slate, which is putting a web services layer on top of the high energy physics workflows that are used by the Atlas and CMS instruments at the Large Hadron Collider in Switzerland. And they have an automated workflow that grabs data and keeps a database of what's running on Frontera and uses it as a backend for that. So in this case, we see what I like to call HPC as a service. So it's no longer about interfacing with humans, it's about interfacing with machines. I think that's a trend we'll see more of. But again, you can't give a talk in 2020 without talking about the coronavirus. I hope one year that changes sometime soon. But at TACC, we've spent, and this is again, one of the shifts we see in the mode of how machines are used and HPC is used. It turns out that this is a public health crisis and a scientific crisis in many ways, but that also makes it a computational crisis. And there's a lot of ways we have computational approaches to attack a global pandemic like this. At the most fundamental level, and I'll show an example of this, we do structural modeling to get basic insights into how the virus functions, and then you feed those into drug screening pipelines to build vaccines. At the opposite scale, from the sort of nanoscale where we're doing viron modeling, we do epidemiology modeling, where we're essentially modeling people and society and how they interact and exchange. A lot of cell phone data tracing, more again, AI and analytics in that part where the unit of model is a person instead of a proton. And then there's somewhere in between, we do a lot of genomics modeling, which again relies heavily on AI about understanding the evolution of the virus and what it is related to and how related medications might work, and then and how it affects different parts of the population differently through host response analysis and epitope analysis. So, and we have ended up devoting, Alejandro showed a couple examples of this, but we've supported about 51 projects. The Office of Science and Technology Policy, along with IBM in the United States, pulled together a COVID-19 HPC consortium. It has since been joined by UK and Japan and a few other places around the world. And we've that consortium and all the cloud providers are in it as well. And of the 134 projects that they are currently supporting related to COVID, 34 of them are on the National Science Foundation resources, and 28 of them are at TACC, 18 of them on Frontera. Our largest machine, we've put about 10 million node hours of time into this. And again, about 30% of our people and resources through the spring and summer. It's actually started to go down as many things have made it into clinical trial, and the sort of nature of that work is shifting. But let me talk about our two largest projects related to that just briefly. And so this is work of Romy Amaro at UC San Diego in California. And this was massive, what we call whole viron modeling. This is focused on the spike that you see here. And this actually, the first spike runs, we started on February 27th. And this simulation is from about April. Again, it was, we went it up. The one spike is 1.7 million atoms. We've scaled this to the whole viron at 200 million atoms. 200 million atoms to do, we need to do about 4 microseconds to get, you notice how it sort of wiggles around over time and it oscillates, and that turns out to be important. So to get 4 microseconds of that, we could do 60 nanoseconds a day on 256 nodes, but to do the big simulation at 200 million, we use 3,000 nodes for about a month to put this out. So it's really a massive scale problem. And so initially we were characterizing the virus. Romy's more recent work, this was just published about 3 weeks ago. So in this, the sort of dark blue that you see covering up the spike here, sitting on top of the virus, is all sugar molecules. And essentially what Romy's team has discovered is the virus, and particularly the spikes, hide themselves in sugar, so your immune system can't find them, right? It's called a sheath of sugar. And what you see happens as it oscillates is that spike on the top, if you look at the left-hand picture here, that spike sort of pops out of the sugar as it oscillates through that 4 microsecond cycle, and then hides under the sugar the rest of the time. So it's awfully hard for a drug to sort of connect with this and cover up that spike. But when it pops out like this is when it can penetrate a cell and actually infect you. And so this whole sugar sheathing process, as it's called, is one of the more recent insights. We've gotten into sort of the basic structure of the virus. And one of the reasons it's good at replicating because your immune system can't find it, and hard to target because of this coating of sugar that lives around the head of the spike. And is relatively unique to this particular strain of coronavirus. So, so this is sort of the basic structural insights we get through HPC. This feeds into what was our second biggest problem, and this is from Rick Stevens at Argonne National Lab with Arvind Ramanathan, who's the PI for this effort, but it involves Shantanu Jha at Rutgers, Peter Coveney at University College London, altogether about a dozen universities and 5 national labs. Have been working in this space of doing the drug pipeline and the computational piece of that, where synthesis is what happens upstream of clinical trials, where medicinal chemists take over and actually try and build something. But before that, we sort of figure out what compounds are possible. You figure out if they can interact with the virus in any way, and if they can interact with the virus, are they toxic? And then once you've gone through those 3 phases, and this starts at about 4 or 5 billion compounds, and we try to end up at about 30 that you try in the lab. All of these upstream stages are done computationally, traditionally through molecular dynamics, but now through a combination of molecular dynamics and AI. So another one of those problems where it's not simply large-scale computation, it's a combination of things. And in fact, data integration as well, because we're taking, in Rick's work here, we're taking the simulation that Romy Amaro did as the all-atom model of the virus, and we're combining it with some cryo-electron microscopy data from experimental confirmation, and then building through an AI pipeline this sort of continuum scale model where we take chemical databases of the 4 billion molecules that we know can be made to be stable. There's actually quintillions of possible molecules, but and through the software framework called Candle, we go through the canonicalization, which is the process, the compute part is called SMILES. You sort of run a computation to get for each molecule how it sort of moves around, and then you figure out some features. And then we use deep learning to reduce the number of those that you actually have to screen and feed into the funnel. And again, this allows us to accelerate the work because these screenings are still expensive computationally to do. And again, started with 4 billion molecules, ended up with 30 that were handed off to medicinal chemists to work with. And some are now in clinical trials. And this is methyltransferase here is one of the top hits that came out of that pipeline. There's actually 2 of them here, one from the zinc database and one from this DB0 database. It's not zinc, that's the name of the database, not the molecule. And this is the rough structure of that molecule, the arrows showing sort of directions of motion. But this is, I think, a great example of how we use still physics-based models that don't go anywhere in the age of AI, right? Because you have to enforce physical constraints and put ground truth in this. In this case, the physics is molecular dynamics, but then machine learning to do optimization and apply policy to that to reduce the amount of computation, and then reinforcement learning to feedback. So it uses a code called OpenMM that sits on top of Ampere in this particular case. And there's been a lot of benchmarking of this. And again, this involves systems around the world. I think in the pipeline there, it showed Frontera, which at TACC, and then Summit here is the machine at Oak Ridge that Alejandro mentioned. Number 2 in the world. Theta is Argonne's biggest machine. And we use some newer GPUs from NVIDIA, and we started to benchmark various pieces of the pipeline. And this is from Chateauneuf at Rutgers, but Frontera did the SMILE computations, which is single molecular input line something. It's a long acronym for basically characterizing the physical structure of a molecule. And it's to allow us to do a docking computation to the virus. And so we could do 20 million SMILEs an hour on 100,000 cores of Frontera. So, and in fact, that again, Frontera is a more CPU-based machine, and so it was best at the SMILE computation and outperformed the other machines. The MD code, the deep drive MD, which is the AI piece, naturally ran better on the GPUs, and so that got pushed to Summit over time. Although for a while, both machines ran the whole pipeline, and then some smaller machines where you could just get down to 6 GPUs and 40 cores. We could do on Summit or on some other machines for the upstage, but do the SMILEs on Frontera, the deep drive MD on Summit. So we had 2 of the, at the time, 5 largest machines in the world sort of combined with most of the machine to look at this pipeline over time. So if you think about workloads about like that and the systems that use it, what is, sort of the first section here, the state of things today. If you look at the top 500 list of big supercomputers, most of them still use traditional CPUs. But if you look at the very largest system, it's much more mixed. About half the top 10 use GPUs. In fact, if you look at all accelerators, it's, I think, 7 of the 10. Today, if you look at these AI and molecular dynamics type apps, for the most part, they have a huge performance on GPUs, but there's still some entry barriers in programming for things like partial differential equations with adaptive mesh refinement are really tough to get onto GPUs well. The Tornado code is an example of that. So there's still a mix of GPU codes and CPU codes out there. Mostly in the HPC world, we assume that there's a big shared POSIX file system that can do concurrent open and close and access semantics correctly and maintain sequential consistency. The commercial cloud, by contrast, usually doesn't have a big shared, at least permanent POSIX file system. You can do it per instance, but they mostly use object stores. Most of the HPC systems in the world today use some sort of low latency, high bandwidth interconnect. Most of things built for the cloud rely on Ethernet. So they think about sort of microsecond latency instead of 900 nanosecond latency kind of thing, or 50 microsecond latency in the case of Ethernet. So a lot of the cloud apps of today don't really need that high bandwidth interconnect. We're beginning to learn with things like that QPT example that Alejandro put up is model parallel AI, where you have these big things and have to distribute across nodes. The interconnect demands are actually higher than traditional HPC apps. So suddenly there might be this great leap forward in interconnect as a result, but they're looking at having 4 to 8 times the bandwidth we typically even have in HPC. If you look at sort of the software side of things today for HPC apps, we're designing a lot of the big systems in the top 500 around what I would call HPC applications, which are mostly C++ or Fortran for the base language, and then parallelism through MPI for internode, and then on node, it's CUDA or OpenMP or open virtually any other set of letters in any language that you can combine. It's open something. But there's OpenMP and OpenACC and OpenCL and open this, that, and the other thing. But there are many standards for doing sort of the thread level parallelism. And again, this assumption of POSIX in a shared file system. And that's what I would call your traditional HPC app. There are many sort of emerging apps, mostly that didn't start at scale, but are finding out they need to scale now, that are based largely in Python. Certainly, at least for the glue between big blocks of optimized C++ libraries. There's a lot of Python, a lot more things like Jupyter. If they've been built for the commercial cloud, they believe in checking out data from repositories, usually implemented in object store. And then if you look at the class of AI apps out there, they sort of lean towards that latter sort of cloudy model where it's Python in all caps and a tiny little bit of every other possible language for AI. But Python is by far the dominant one. And fortunately, I think in a lot of ways, because this gives us something we can work with in performance optimization, there's just a few dominant frameworks, TensorFlow, Keras, and PyTorch, that make this up. So that, I would say, is the state of the art. Let's talk about what's happening in technology that changed this. And I sort of want to pick up where Alejandro ended his talk, talking about Moore's Law. And our technology drivers, really, there's just two, and there's a million implications of these. But one is Dennard scaling ended about 15 years ago, which is power per transistor as they get smaller, which had everything that everybody wanted from Moore's Law. And Moore's Law is probably ending soon. So I would say, Alejandro had a graph, but the graph of Moore's Law is probably the most used graph in the history of PowerPoint and all presentations in the universe, but also, I think, not well understood for all the times it get used. So Moore's Law is about transistors per square centimeter. So, if you look at in a single device going back to 1970 or so, and actually on the next slide, I have data points out to 2018 with the same graph, but you see that we're basically on the right, this is the Moore's Law curve, and we're still pretty much on it. There's been a little bit of inflection here and there, starting to tail back this way. And the last couple of years, as we've missed new process steps, it's starting to fade. But mostly we've been on Moore's Law. But something happened in about 2004 that ended all the good things we got out of Moore's Law, which are these other curves, which is how fast a single thread of code goes, what the clock rate of the chip is, how much power the chip uses. And all of those right about here, 2004 is when Dennard scaling stopped and leakage current started to overtake operating power. And as the devices got smaller, so we stopped getting faster, smaller, we got smaller transistors, but they weren't sort of faster, more power efficient transistors. So we stopped scaling frequency. And when we stopped scaling frequency and the performance of individual threads of code went up, they still wanted to say servers went faster. So we saw multi-core, right? Because we had more transistors, but we couldn't make them go any faster. So we started replicating them on the chip. And you see the number of cores, which was basically one per chip, from 1970 to 2004, started expanding, and this hasn't flattened out as much as they thought. And now we see these 80 and 128 core chip designs that have started to make it out there. So Moore's Law has been on track, but the good things about Moore's Law have stopped for a while now. As we think about exascale computing, this is same chart, a few more years of data, so you can see what's gone on. And that, again, through 2018, still scaling the transistors, still not scaling single thread performance. It started to come back up because we've given up on power and started to let that go up. For about 10 years there, we said sockets would never go about 130 watts. Frontera is 210 watts per socket, and we're planning for 350 in future machines to get some of this single thread performance back. Cores have continued to increase. But the thing that's hidden in this as well is these are how we've changed the hardware, but it's had serious implications for software. As we've gone to these sort of heterogeneous and highly parallel individual chips and nodes, we've broken the sort of relationship to software and how it scales in performance and cost. If the next generation of chip, the single thread performance went up by double, your software performance probably doubled. If you just double the number of cores and your software doesn't take advantage of that, then your software performance stays the same. And you have to spend a bunch of money on the software side of the equation. Although there's some tricks to mitigate that. So this has really been a shift that I don't think everybody's really internalized yet, even though it's been going for more than a decade in terms of what's happened there. And that's just the facts of technology. And in fact, if you look at the past decade, if you go back a few decades, it's even worse. We used to get a lot from compilers and a ton from process technology, and they're all getting smaller. So we still, over the last 10 years, if you look at the performance of a socket, to keep this sort of fictional Moore's Law, where we can say the peak performance of the socket has continued to double every couple of years, we're getting about 40% of that from the physics, from the process technology getting better. We've gotten 8% recently by just saying, to heck with power, we'll let it go up, and by making the die bigger. So we've compensated for the fact that we can't scale the process by saying we'll just do bigger and higher powered chips. We've got about 17%. These are the improvements that have come from things like the vector organization that Alejandro went through in detail. Microarchitecture improvement. We've seen about 15% from power management. If we can power down some transistors, we can run the others hotter and get more performance. And unfortunately for conventional CPUs, we pretty well understand compilers. So we've only gotten about 8% out of compilers. Recently, this is not true on GPUs and some of the other new architectures. So the other thing, of course, we're seeing and why we think Moore's law is ending is that we're having trouble making the node size smaller. Part of it is it also doesn't mean as much as it used to. So if you look at the Intel 10 nanometer process, and Intel has been much criticized and perhaps deservedly so recently for constantly delaying 7 nanometer. But if you look at their 10 nanometer process, it's 100 million transistors per square millimeter. And if you look at the TSMC, that's the Taiwan process that fabricates a lot of the ARMs and the AMD chips and the GPUs. It's 91 at their 7 nanometer process. They only get 91 million transistors per meter squared because feature size is not everything. It's how you use that feature size in terms of implementing devices. So, there's a group in the industry pushing to move towards this LMC measure, which stands for logic memory connections. To go away from using 10 nanometer or 7 nanometer, one, because it's just not going to change as fast. But if you wanted to compare those two processes up there, you need to look at the density of logic, at the bit density of memory, if you're building DRAM, and the density of connections between the memory and logic. Because you can build really fast transistors and you can't actually connect them to anything, you just starve them, and it doesn't do you any good. So we may need to look at new process. Given that we're at the end of Dennard scaling and approaching the end of Moore's law, what can we do about it from a hardware perspective? Well, from my perspective, there's sort of 4 things we can do, right? One is try and squeeze out more life from the current things by continued innovation and some rebalancing in hardware. One is specialize, how we use those many transistors that we keep adding to the chip. Another is to disaggregate, which I'll define in a minute, or we can just change the paradigm completely. So these are sort of the 4 directions, and I think we'll go a little in each one and more of that. So one thing we know pretty well is that we starve our current chips for memory, right? And if you're just doing some Gordon Bell analysis this week for the ones that are being selected at supercomputing a month from now, and even those very large scale, the Gordon Bell Prize goes to the largest and most significant computation every year. Some of this year, as you might imagine, are around COVID, and there's some other topics up there in AI. If you look at the percent of floating point performance they actually get out of the chips that they run on, even these, best in the world ones often get less than 5% of the peak performance of the chips. And one of the big reasons for that is memory. And we just can't feed the transistors fast enough. So, and in fact, in the Fugaku system and the new ARMs that Fujitsu is building, one of the big things there is they put high bandwidth memory onto the package. So essentially, also using that sort of multi-die technology that Alejandro mentioned, we can stack levels of memory onto the package, right? So inside the pins of the chip, you spend an awful lot of time getting across those big metal pins from tiny little transistors off the chip. So this notion of packaged high-speed memory, I think, has been one of the primary advantages that GPU has had. Some of it is architectural, but a lot of it is the fact that the memory runs better. So, and so with this new ARM, we can actually get new bandwidth, and that's one of the things driving performance up. So if you look at the best current Xeons or even AMD chips per socket, the memory bandwidth is about 200 gigabytes a second. If you look at that Fujitsu ARM that's in Fugaku, it's a terabyte a second, so about 5 times better. The trade-off there is that you have less capacity. They only have, I believe, 32 gig for 48 cores, whereas, for instance, on Frontera, we have 192 gig for 56 cores, so about 4 gig per core versus 2/3 gig per core. But the bandwidth is higher if you can fit into that space or scale your problem over enough processors to fit into that space. And GPU is about 800 gigabytes per second. And in fact, one of the big GPU advantages has been this high bandwidth memory. So I think a thing to look for is more HBM and many more chips. And ARM has really been leading the way on this, but I think we'll see it in a lot of places. So that's one way we can squeeze out more life is package memory and stop starving the silicon we had. There's some other things. Alejandro also mentioned bigger and denser nodes. So you can use coherent onboard interconnects to make your single servers bigger, right? We stopped scaling the transistor, we started putting multiple cores on a chip. If we stop scaling the chip, we can put multiple chips on a node and treat it as a single chip. So things like NVLink from NVIDIA or CAPI from IBM, and there's an Intel equivalent, of course, create a coherent memory address space for a heterogeneous node of CPUs and GPUs or many nodes. Unfortunately, we've been down this road with building big symmetric multiprocessors, shared memory machines of the 1990s, and you get to 32 to 64 chips, and you can't maintain coherency across the network, and the engineering cost of keeping enough traces on the motherboard goes up. And so this is not an unlimited panacea of future performance, but it's going to help in the short term to build, 8 GPU, 4 CPU nodes, in a single box that we can sort of treat as one processor. Again, there are software challenges, and we'll get to those. So the other option here is to use silicon photonics or other high-speed interconnect connections in the hope that you can bring this off node and create this coherent interconnect at scale, but we're going to need multi-terabytes per second instead of the current like 200 gigabit InfiniBand to get on and off. And I mean terabytes, not terabits there. So, and the other thing is you can change the architecture, right? So there's the, what's happening broadly last year in the industry is doubling down on the GPU approach to get the headline flops right. So you see Intel and AMD desperately chasing NVIDIA in the GPU space, but they're also going to change the programming model a bit, which carries more risk, and we'll come back to that. So, and then finally, how are we going to push that process, even though the process is slowing down? 7 nanometer is sort of here, 5 nanometer is visible, 3 and 2 are the next ones. It may be tough, but there is an industry group, the International Roadmap for Devices and Systems, IRDS, that has pushed how we might do this. And part of it is we're going to have to change transistor designs from the FinFETs we use today to nanowire and nanosheet technologies for building transistors. Things called GA FETs and other words I don't really know, but there is hope of how we might build these 3 nanometer and 2 nanometer transistors. It's probably going to take an extra year per process to get there because we're changing more than just the process. We're changing many new technologies go into getting that voltage down. We will see some improvement, but I think regardless of how that plays out, the power is not going to go down enough per device for us to get back to the good old days where you just buy a chip 2 years later and your same code runs twice as fast. It's just not going to happen again, but we can get something out of the process. So, so there's ways that we're going to keep going. CPUs aren't going to disappear overnight. But in the long term, there's huge challenges moving forward. So the next thing you can do is specialization. And these slides I have stolen from John Schauf at Lawrence Berkeley Labs. I think I credit him somewhere, but in nature, if you have a resource limited environment and you need more performance, you start to specialize, right? So if you want to build big general purpose, you can build an eagle, right? Which is a bird, if you want to maximize power, speed, ability to kill fish at a distance, you build eagles. And you can think of the Xeons or the AMD chips of today as being these sort of big cores. As the Dennard scaling stopped and we just had transistors we didn't know what to do with, well, if you can't feed an eagle because you don't have a fish to give it every day, and you have limited resources, but you still need birds to eat a lot of insects, you start building a bunch of sparrows that are all the same, but you have a lot of them, and maybe collectively they can eat as many bugs as one eagle can. And that was the Intel Knights approach, and AMD multi-cores and the earlier Cavium Marvell chips, as well as the GPUs, were sort of, let's build sort of homogeneous but smaller, thinner cores. And then as we have even more transistors, you start to need to say, well, there's really niches in what I need to do, and not everybody runs the same algorithm. And we start seeing this sort of post-Moore's law customization, and you see this in tons of chips now. The Amazon one, Alejandro already mentioned, but Google and Apple and Samba Nova and many of these startups are all in this sort of specialization thing. So, and I think it's sort of feeding up to HPC from first mobile and now laptops. So you saw the last few months, Apple announced a switch to their own chips for laptops. And if you look at their current chips, more than 50% of the silicon era is in special purpose accelerators on those chips. And I think Apple's app ecosystem makes this possible, right? If you want to use the gyroscope or the camera or the microphone and you want to do text-to-speech processing, you have to use their APIs. So they control the software. And if they control the software, they can start taking these software and API features and implement them in hardware, because every phone uses the microphone and the camera fairly frequently. So just build special purpose hardware for that. And so they've slowly been moving API functions from software to hardware in a way that the programmer can't see because they control the APIs. And it's happening faster and faster. And so this is the Apple, and again, IP reuse from ARM. You know, they build this based on the ARM idea, and then they take that ARM and then they add these number of specialized blocks. And if you go back just over 8 years, right, they went from having 5 or 6 accelerators, you know, DSP for the camera, to now having 40 in the silicon. And they hope to do this in laptops too. And, you know, here's sort of the layout of some of this, graphics processor, et cetera. You know, if you look at this, you know, this is the actual chip area. So here's, you know, a few CPU cores, here's a few more CPU cores. This is all memory. This is interface to get to off the chip. This is the SDRAM interface up here. And then here's all the crazy non-core accelerators. And you see it's bigger than the cores at this point on the chip. So this has happened in the mobile space, where power is already a scarce resource because they have to live on a battery. It's now happening in the laptop space, and it's reasonable to expect it could happen in the server space. And this is the chip that Alejandro mentioned, the Graviton at Amazon, right? So, you know, more performance. They're starting to customize the chip for the workload that they have, right? And they're saying, hey, suppliers, we're not going to wait on you to do this. We know what our workloads look like, and we're going to customize chips around it. Now, a problem with this is that it can be expensive to do, and Amazon has the resources. For the rest of us, it might be harder. So we need to think about what this might mean from a software perspective. So again, I actually credited John here, shamelessly stolen from John Shelf, at Lawrence Berkeley Labs, because he'd already made nice charts and I didn't want to do it again. If you think about how we build things for a standard CPU, right, you know, we're constantly in this architectural model, and this kind of code has to work. Increasingly, you see these data flow architectures, right? FPGAs can do them, but we can sort of customize those more into what are now called CGRAs, the coarse-grain reconfigurable arrays. And that's what the Graph Core and the Samba Nova and the Cerebrus chips do. And say, hey, 64-bit functional units aren't necessarily required for AI and some of these workloads. We can use smaller grain, you know, 8-bit and 16-bit ALUs to put together, but still allow us to build very dense grains and think of this as a data flow problem. And unfortunately, again, this involves disrupting software, which is always dangerous and expensive. But if you'll pay the price through software and map, again, this is some work that happened at NERSC with some folks at Carnegie Mellon, but this is looking at what could you get. I can't remember which kernel, I took that out, but I think this is a density functional theory kernel, which is 25% of the workload on a lot of modern HPC things. And they took that kernel and they spent the ridiculous amount of time on it, and they used a Samba Nova chip as the test. And, you know, here is, you know, if you say that a CPU is 1, you know, a GPU could give them maybe 3x that. The first pass through the tools for Samba Nova gives you 6x. Once you figure out how to optimize the kernel, you could get to 60x or 20 times the GPU at roughly the same power. So the potential for performance is there. The software experience is expensive. So we'll get to that on the science side. So third thing we can do is disaggregation. And just go through this quickly. Our current machines assume that the basic unit is a server, and a server is this monolithic block of processor, memory, storage, and maybe one or more accelerators, depending on how your in-server interconnect looks like. And if we can get the silicon photonics to get fast enough interconnects, and if we can interpose them between these components in the right places, we don't have to put servers together that way. And so disaggregation is the notion that, say we had a rack of servers or a rack of processors, and then we had pools of accelerators and pools of storage devices that we could dynamically compose in the rack into different classes of server using the same base set of hardware. And this notion is called disaggregating servers. And so Again, stolen slide here, but just think of the AI problem that the cloud guys face. You know, there's a write node configuration for training. There's a write node configuration for inference. There's a write node configuration for data mining and a write one for graph analytics. And they all involve completely different kinds of hardware, right? Different tuning of memory, different amounts of storage, different numbers of accelerators per socket of CPU. And so you can buy 4 kinds of servers and try and, you know, route workload across your data center to each one, or you can buy these basic components, GPUs, CPUs, storage devices, and links, or high bandwidth memory links perhaps, and then recompose them based on the workload. And so this seems to be a trend that's coming. It is in the market now. Liquid is the first to market in this company, LIQID. And this is their notion of having CPUs, SSDs, NICs, and GPUs aggregated through this liquid fabric. So the current fabric they're using is PCIe. Gen 4 is out now. PCI Express is a good fabric, but not a great fabric. And it means you have some latency limits, although better than current interconnects. And you have range limits, which is why we have stuff like InfiniBand and Ethernet instead of using PCI everywhere. Is you can run the cable about 2 meters before you're going to have cycle problems. So basically, you can do it in a rack. You can't do it across a data center. But this is available today, and it's starting to appear in large HPC systems. And there's numerous research approaches that you can find in silicon photonics that talk about these multi-terabyte interconnects. That can mean that, you know, if Liquid can make the logistics of this work, it's hard to schedule, et cetera, then some things can happen on this. So that's sort of the disaggregation story. And then the fourth thing we can do is just throw out that paradigm altogether and do something in quantum and neuro-inspired. And I will say that while there is a huge amount of promise here, and it's, you know, we could spend hours just talking about this, it's still a niche thing, and it has enormous software costs to change. So I don't think much of this will happen at large scale anytime soon. Digital will still be there, but these other things are emerging and worth mentioning about. So, and we could do the same story on storage, but if we just think about processors, we're seeing sort of increased power per socket, sort of a reduced return on investment and performance improvement each generation, memory bandwidth where we can make big improvements, new architectures out there like these various array processors where reduced precisions will play a large role. I'm not going to have time to talk about cooling, but all of these have implications for how you cool them. So that's what's going on in technology. In less time, since I've already used about 45 minutes, let's talk about the science part of this and what drives it. So, you know, the COVID work this year has been what I would call urgent computing, and it's been a big part, but there is tons of evidence, and again, Alejandro showed many use cases that the demand for HPC is higher than it's ever been. And you can pick reports from US agencies and the national academies that talk about the sort of driving demand for this and the future of computing. The Office of Science and Technology Policy just did an update on the National Strategic Computing Approach. And they all say computing more and more and more. You can do this by discipline. And if you pick any paper in any field and you talk about grand challenges, and I have physiology and brain science and wind energy in this and environmental fluid dynamics, but pick a topic and you find their grand challenges paper, and I guarantee you'll find 30 to 50 uses of computing and data in those papers that say that in every field of science and engineering, this is demand. And that's before we even start talking about AI. And now there is a report of the month on how machine learning will influence science. So, so there's tons of demand as the baseline, but the demand is changing a little bit in nature. And this is back to some of what we talked about before, but there's what I call the outer loop problems that I want to dive into a little bit. There's the cheap data, and then AI, both the current deep learning and the things that are going to happen. So let's talk about outer loop problems for a minute. And I should have put in more examples. This could be an hour-long talk in this slide all by itself, but we've really reached a period of transition in computational science and engineering, right? And so we see some problems like Lee's tornado problem that I showed, where we're still getting benefits of just scaling up. And fortunately, there are still a lot of those problems where a bigger machine will give us new physical insight, period, even if we don't change the way we do science. But we see other things like integrating cryo-EM data with molecular dynamics with machine learning in the COVID pipelines, in linking hurricane forecasts to storm surge forecasts, which we're running today. So there's a category 4 in the Gulf of Mexico headed for Louisiana. Many of these problems where we're trying to link across scales, across different types of physics, across different timescales, so multi-rate, putting together these different models, the storm surge with the weather, with the freshwater rainfall to get flooding. And all of these create this sort of 10 to 100 scale up of the amount of computation we can use. The outer loop problems are things like if you want to say, well, we're doing our storm surge today, and we want to take actual data from wave height buoys and put it into a running simulation. To assimilate that data, you have to do an inverse problem. You essentially have to solve it in reverse, which involves solving it forward at each data point and then doing it backwards once. And that can give you 1,000 times the amount of computation. If you want to do uncertainty quantification, you have to tweak all the input parameters and rerun the simulation. Again, hundreds to thousands of times to understand the uncertainty bounds in your model. Again, if you want to make your hurricane forecast better, we have to tweak the inputs because we don't have exact numbers for the state of the world. So data assimilation, inverse problems. If you want to do optimal design, you have to sweep through the parameters and again, do hundreds of runs of the same scales decision. If you want to control a tokamak reactor, if you want to do simulation-based decision-making, basically you're running through a list of parameters and all of those, and that gives you hundreds to thousands of times more computation. So that we have to do. And a lot of what we want to do is understand better the uncertainty in our models and do data assimilation and things like that. So, and then of course, machine learning keeps driving that. So a little on data, I think this is fairly obvious, but it still bears saying. We have many, many kinds of sensors that produce data. And our biggest problem is they get cheaper every year for the bytes that they produce, right? And this can be the Large Hadron Collider, or it can be a traffic camera. One traffic camera is not an HPC problem. Model near miss collisions from every traffic camera in a country. And if you have 100,000 cameras, that is an HPC problem. So from satellites to sampling internet traffic, we can get a lot of bytes for almost no money. And the inflection point that's happening now is 5G, which means, every field of science wants to deploy many, many low-cost sensors into the field, whether it's precision agriculture, putting a sensor on every tractor and in every soil moisture for every row of a crop, or it's a traffic camera on every corner, or it's a water quality sensor at every stream that feeds into a river, and tens of thousands of those. You can put them out there. You can move an awful lot of data wirelessly for virtually no money. And there's a lot of work in edge to reduce this data. But for every edge server doing data reduction, you're still going to a data center in a big system somewhere to process that data. And so this drives us up. And then the fact is, this is really what drives AI, is all this data that we can get doesn't necessarily follow well-organized governing equations. Genomics was our first test case in this, right? There's no differential equation to say that this, having a guanine in this position in the genome means your eyes change color. There's a statistical model that can predict that, however, if we look at enough data. So we're going to have, camera data where you have bad angles and have to correct. So many cases of this, right? We're going to have data of lousy quality with a lot of noise in it and no metadata that we're going to have to infer. And we're going to have to build this in statistical models. So if we can't model it with physics, we model it with statistics. And that basically is what we're calling AI. And so currently this is mostly deep learning, big, deep convolutional neural networks. There are lots of other techniques out there that will probably assert themselves at some time in the future. But again, Alejandro showed the QPT example, 175 billion degrees of freedom in that problem, right? So, we do our big hurricane simulations with a few million degrees of freedom. So this is going to make our toughest physical simulations look simple coming forward. So all of these are driving much more computation, much more tightly coupled. And then finally, it's how people actually want to consume this. So there's a few changes in sort of, I would say, the social contract of how we deliver high performance computing. One is this notion of urgent computing. The other one is just, what I'll call being old and grumpy, these kids today. But essentially, the age of the cloud and cell phone experience is new programming models for the ones that program, but the cloud internet experience. Hit buttons, have things respond instantly, which is not the mainframe experience of hand off a deck of cards and get a result tomorrow. And part of that is the nature of how they want to experience. Part of it is just that data science and AI, as we do it today, is almost inherently an iterative and exploratory problem. And frankly, simulation is too, but we've just sort of adapted to the fact that these experiments are hard to run and take time. And it's from people who are used to doing bench experiments, they're hard to run and take time. But if you're going to sit and do hyperparameter tuning, if you want to sit and explore a data space, you're kind of, you can't automate the things you want to do because you don't know what they are until you see them, right? You want to sit there and explore. And that means different sort of service levels. And then finally, we have this amount of complexity that's becoming unmanageable. So to dive down into those a little bit, first, there's the urgent computing. And that is just the fact that basic research, where we have a lot of time to spend decades understanding the fundamental nature of black holes, is not the only thing HPC is used for nowadays, right? Severe weather forecasting is the classic example: tornadoes, hurricanes, floods. In response to all kinds of disasters, we now do real-time modeling of wildfires. We do, which buildings do we need to send inspectors to after an earthquake based on fast flyovers and image processing, right, is an AI HPC problem. How does a chemical spill move through the air? There's a whole bunch around the BP oil spill in the Gulf that we responded to. Pandemic response, again, a third of our workload this year has been in pandemic. And this means we have new service levels required. We can't wait for the queue. We can't take maintenance windows. If you're running a tokamak fusion reactor and you want to predict disruptions in the plasma to change the control streams on it before it explodes, that has a hard real-time constraint, right? It's not put it in the queue and hope for the best. So this changes a little bit of how we have to deliver HPC. The second thing I want to talk about is the complexity. So everybody would like this nice cyber infrastructure where you push the button and it happens. Perhaps on the cloud, you rapidly discover that there is no cloud. It's just computers with all their problems that somebody else happens to own. And you have all the same problems. And there's several providers for that, each of which I think Amazon's full service list now takes 40 pages to print for all the different things you can get. And it's confusing enough. So my colleague, Nirav Merchant at the University of Arizona, put this slide together. So he gave a midterm question to his students in a cyber infrastructure and genomics class. And he says, all right, you have a 10 terabyte data set. I'm going to let you process 1 gigabyte of data. It takes 1 hour and it produces 100 megabyte of output. You need a gigabyte of RAM to do it. You can split the input of the 10 terabytes and run it in parallel. Take the AWS calculator. Assume that you have to finish this in an hour. How much does it cost? So the answers the students give have a low of $16, a high of $218,000, and a mode of $10,000, and none of those answers are right. So the cloud is almost unmanageable in complexity today. And when you start thinking about the software services to do these workflows with AI and physical modeling put together, a colleague at Illinois put together with some folks at a couple of companies, and it's supposed to organize and explain the big data landscape of software tools today. I think the only thing it usefully does is gives me a PowerPoint slide to explain that the landscape is way too freaking complicated today. And nobody knows how to use all these things, right? There are literally thousands of tools in this graph doing, across infrastructure, applications, et cetera. But, how many kinds of graph database does the average person know? So it's just enormously complicated, and that produces some awfully big challenges for us. So our theory has been that containers will solve our software engineering problems. This is stolen shamelessly from Torsten Hoffler at Switzerland. Thank you, Torsten. But he put out this slide recently, and I just love the containers falling off the ship here. And he's like, look, we talk about good ways to develop and maintain software. We don't even know how to run it anymore, right? We used to have all of these problems with dependencies, and we've said, you know what, we're just going to throw it in containers and it's going to work. But that's allowed everybody to give up on doing good management. So, so now to run a particular container, he needs 4 versions of CUDA and 3 versions of GCC installed, and they all have a different driver interface for the hardware. And so everything falls apart. So as my phone starts to ring, apologies. And then let's take this and make it heterogeneous, right? This is just for normal processors. So this is one of our software management problems is containers help, but used blindly, they can be deadly. And deadly to performance, and we'll get back to that. And then there's the fact that there's a lot of things in theory we'd like to do in computational science, but the gap between what we can do in software and what we actually do is huge. And the example I was using here was some work we did with epidemiologists, where we started with a dozen MATLAB scripts that they sort of ran by hand to do pandemic modeling. That then needed to be run for hundreds of cities every day and integrated and scaled out to terabytes. And so now it's an automated set of C++ code that runs from a portal. But there's an XKCD comic that solves every problem. And this is the one that we see. And I deal with something related to some version of this almost daily. I have 9 terabytes of earthquake data and I don't know how to use SFTP. That was one from this week. But what we'd like to think we need to help scientists with in HPC is, our data is really complex. Can you come up with patterns? We'll come up with these fancy machine learning algorithms and it will be extracted. And the other side of the panel is what we actually see. It's like, well, our lab was infested by wasps for a while. And we had to take pictures of all the equipment through the window. So can you help us get Polaroid pictures of graphs into an Excel spreadsheet? And this is a lot of the real work of doing computational science today, and scaling this up into a magically abstracted, highly heterogeneous environment at millions of cores is complicated and not as simple as saying we have the tools to do it. So, and that leads me to the tensions that all these things create, right? So we want urgent, on-demand, and interactive computing are all words that somehow mean the opposite of a highly and efficiently utilized computer. And everybody who buys a $10 million computer would like to see it be highly utilized and optimized. All of this heterogeneous hardware adds complexity to our software. We have outer loop problems that add complexity to software. End users hate complexity in software, right? We can do great things in vectorization. For any of you who have people working on code, after your grad students get the code working, how many hours do they spend making sure the vectorization works? And that's assuming they're in a language where you can actually expose vectors and not doing tensors in Python. So abstractions exist to hide complexity. But abstractions also lower performance, and we're not doing lower performance computing. We want to do high performance computing. So how can we build abstractions to do this? So with my last couple of minutes here, I just want to say, what can we do about these things? And there's a ton of exciting directions out there. I mentioned some of them in the hardware section. And this list is far from comprehensive, but all hope is not lost. It's just hard. So there's specialized hardware out there that can work if we can extract good primitives. If all AI stays based in TensorFlow, then all we have to do is make TensorFlow operations work well, not generally solve the computing problem, which would be awfully useful. If we can build good libraries on top of that to extract good primitives, if we can disaggregate to do customization, then perhaps we can actually get performance out of them. Containers as they exist are a mess, but container recipes in the Open Container Standard that aren't binaries, but just the list of instructions to build and install can remedy a lot of this, because then we can build platform-specific containers from the recipe and the repo, and that's actually how we use containers in our work now. But we're still going to have to invest in software and engineering to do this. AI can help us build the cyber infrastructure to do this. I didn't even mention optimizing chip layout in this, but we can do the metadata extraction for bad data. We can do the performance analysis and tuning of our systems via AI. We can hopefully do some of this complicated heterogeneous workflow composition. We can find faults. We can use natural language processing to specify some of the work rather than code. And I'll show an example where we're doing some of that. We can build comprehensive but still domain-specific platforms across scales to manage this complexity. And as we do that, the HPC user interface that we're thinking about in the future might not be to the human. It might be this as a service model where we're talking to another machine, which changes the equation of what we have to optimize and how we have to make it easy to use, right? The computational science user interface is increasingly a user talking to a browser, and that browser lives in a container somewhere, and that container runs other services, and some of those services run on HPC. And that's awfully complicated, but it doesn't mean we have to make everything work for every user at the command line anymore, which will help. If we can embed some of these through gateways and other things, it shrinks the space of our optimization problem. The other thing we can do is, people care a lot about power in this, and green can be a driver. The best thing we can do to make green computers is not do careful management of how we schedule the data center or look at better cooling strategies. Remember, we're only getting like 5% of peak in good cases and like 0.01% of peak in bad cases for software. If we could go from 0.01% of peak to 1% of peak, we won't use 10% less power, which better cooling can do. We'll lose 100 times less power. So we can use green as a driver to give us more efficient and more performance software. And we found that software can change. It just takes time and sustained investment to get people to be willing to make those changes. And so I want to show one example in close to closing on how this might look going forward. And this is through a project we do for DARPA, the Defense Advanced Research Projects Agency in the US, called Synergistic Discovery and Design. And this is more or less the AI problem in a lot of ways, right? We're used to using computational design where we have good scientific knowledge and a complete theoretical and mathematical model of what we want to build. And increasingly in the world, we want to do design in the context of uncertainty, where we have incomplete models of the thing we want to build. And biological systems are a great example, because again, there's no equation-based mapping between genomics and phenotype, right? Between expressed behaviors. So this started in synthetic biology. We use the same framework in things like photovoltaic materials design today. But so we had this vision of being this sort of analysis hub where there's 6 data provider teams and 15 modeling teams with us as the platform in between, and to try and enhance everybody. And what has emerged from some of the contractors and just a great group of people working on this, some of whom are at TACC, you know, we've used this to be sort of at the forefront of our explorations into AI and natural language processing and API and interface and how we talk to the edge, right? So this is slightly anonymized because there's a couple of sensitive things in here, but you know, this was, I wanted to run an experiment computationally and with experimental apparatus on these biological circuits. And this was an activator circuit for certain kinds of growth in yeast. And use CRISPR to, you know, edit the genes in yeast to do some of these things. And so the way that we work in this project now is a team of researchers can sit down and use a Google Doc and mostly write in English to describe their problem. And some of this is metadata. The goal is just plain English. Some of it is more controlled. So the experimental plan is a table with format, and this is several pages long. There's places where the outputs go and things like that. But their entire specification of the problem is working in a Google Doc. Right, a familiar interface in something that approximates English. There's things that are controlled. But then you push a button in the interface and say, consume this Google Doc, and there's this whole orchestration of many pieces of code that schedules a robot facility to go somewhere in another state, go make a bunch of robots, actually run this experiment on CRISPR and yeast, upload all that raw data to our repository, process all that raw data using for primary and secondary data products, often using AI, characterize it in the context of all the other experiments that are there. It will populate all the outputs into the Google Doc and put in URLs to where all your data files are, with complete provenance trace of how they were, you know, if they were produced by a robot, you know, where the experiment ran, how it ran. If it's an upstream data product, what's the software pipeline that ran on it? And then finally, it uploads stats into a dashboard for the entire repository that says, across all of our, in this case, biological circuits or all of our materials or whatever it is, you know, take that data corpus and what can we learn from it and get, you know, a statistical analysis of all the data in there. So you get a Google Doc and a dashboard, and behind it, we're orchestrating storage systems and high performance computing systems and, you know, robots and cameras and genome sequencers and, you know, all sorts of crazy machines that make this happen. So, you know, this could be the future of what HPC looks like. And it's not purely HPC anymore. It's HPC as a piece of a broader sort of computational science or engineering workflow. And so the trick is going to be, with all this complexity, managing the evolution of all this, right? So we have huge challenges in the technology and the kinds of science we want to do and in the way people want to use it. But all hope is not lost. To do this, we have to make sure we evolve everything together and not independently. Independent evolution will end up with things that want to compete. So we need to take algorithms, applications, and architectures and somehow manage to evolve all these together. But if we can do this, we can not only sustain high performance computing as the field and for future systems, but we can continue to be the pioneers that HPC has always done for the broader IT industry and AI and the cloud, and hopefully be indispensable for future generations of applications. And with that, I will stop my very long-winded talking, although still I hope on time, and we can move to discussion. So let me stop sharing the screen. So thank you very much.
Thank you very much. I think it was really great presentation, covering a lot of topics, very complex. Okay, let me start the video. So, so about the attendees. So, okay, there is already some Q&A.
Do you want to give me the questions? Or you want me to read them?
Yeah, I think you can check it probably if you click on Q&A icon.
Yeah.
So from Paulo Mateus, I can read it if you prefer.
Yeah, sure. Okay, I see it from Paulo. Paulo Mateus asks, could dedicated hardware be standardized to simplify integration in HPC hardware? Are there many intensively used libraries and methods besides deep neural nets that are worthwhile implementing in dedicated hardware, or are they just a few? So yeah, that's a great question. And so it comes down to a couple of things. One is, can we build chips using good IP reuse and blocks of IP, right? Could the ARM ecosystem expand to have these, domain-specific accelerators to work? So I think one of the reasons sort of neural net chips are taking off is, the tensors that do a neuron computation and neural nets are, well articulated. We know what the primitive is, and we can build a lot of stuff around them. It has been more difficult to do in other fields of science, but I don't think it's impossible. I think we just haven't paid enough attention to it because everybody wants to do things in slightly their own flavor of their own way, right? The place it has worked, Jack Dungara's libraries, right? BLAS, the basic linear algebra things. In fact, tensors are also linear algebra computations, right? So that has been the key for so many things is everybody wants a good version of BLAS, LinPack, LAPACK, something that the basic linear algebra subprograms. And half the industry has been about getting that. It's the other ones. We know there's a lot of FFT, how to make that scale. We know there's kernels and density functional theory that are huge. I don't think there's a set of 5, but I do think there's probably a set of less than 30, which if you could put together as IP cores, that we would hit a lot of these things on, right? Correlating 2 strings. There's, for genomics related work, there are, probably a bigger set than we can put in one chip, but if we could build, a few versions of chips that had different IP cores and combine them in different ways, it's probably a manageable problem. I don't think there's been enough work to identify what they are. So again, I think it's more than 5 or 10, which is unfortunate. I don't think they're easy to suss out because the implementation of software doesn't make it clear what the core algorithms necessarily are. But if we took sort of a base look at methods and the problems we wanted to solve, I think it's a doable problem to come up with that set of cores for specialization.
Okay, I think you can click on this answer live, I guess, to wrap. Yeah, good. So are there any more questions?
I have a couple of questions, but I will say it out loud because I'm not sure I can write.
Yeah, apparently if you're a presenter, you can't also type into the Q&A box. So yeah, go ahead, Alejandro.
Okay. Yeah, I have 2 questions. The first one is on the comment on expanding coherence to large part of the system at some point, like, oh, maybe we could even use the photonics, like optics, to maybe extend coherence beyond that. And that's something that really resonates with me because part of my work is, okay, how far we can scale coherence. My question is, how valuable is in the context of HPC having coherence extended to maybe up to the whole machine? If that was very cheap to implement, for example, what is the value of extending coherence to the largest extent possible?
The value is that it simplifies the programming model, right? If you don't have to worry about the explicit cost of moving data and who has which copy of which variable and is it coherent, we can greatly simplify the programming model for very large applications. So that would be the value. I will say though, I think we can scale it beyond a node. I'm skeptical that we could scale it to the whole machine because of the experience with SMPs, right? If you're trying to cache memory, then Snoop cache protocols get more expensive the number of nodes you add, right? And eventually it becomes just way too expensive beyond, say, 32 or 64 things, right? But so where I think it has value is in the sort of level of doing node disaggregation, right? We're still going to have, we need to build coherent large nodes. So, you know, say I want to take, you know, 16 accelerators and 4 NVMe devices and hook them to 4 sockets, right? With, you know, storage class memory of a few hundred gigabytes for that. You know, being able to build a node block like that and have it be coherent across a wider interconnect, I think makes sense. I think we'll still end up at large scale having to do some sort of, you know, we'll create a coherent block that is a node and then take a bunch of those nodes to build a full system. So I see this as, you know, a rack level, 2 racks level of doing that sort of silicon photonics integration, just because, you know, scaling up SMPs, which was the model for so many companies, that many of which are now gone, but, you know, the big SGI machines of the 90s, the Onyx designs, right? The Altix designs, you know, they got to 32, they could sort of get to 64, and then you essentially end up doing distributed memory with tricks after that, right? So, but 32 devices in a node is a long way from where we are now. So, so I think these interconnects to get us these sort of fat nodes, and so we have, you know, 1,000 fat nodes instead of 20,000 small nodes. That's where we're going to see this notion of coherency be important, and making those relatively complicated nodes somewhat easier to program by having a coherent address space across them.
Yeah, that makes sense to me. Then my second question is on the complexity introduced by heterogeneity, right? We have all these different accelerators, and one of the things that I'm afraid is that the software development resources in HPC are limited, right? Because at the end, the computational part of centers is not huge. Yeah. Do you see a comeback of DSLs or high-level compilers or something like that? That's something that can bridge that gap, or are there other things that you think about for that?
I do. I think, you know, DSLs, for the audience, domain-specific languages, you know, I do think that's the right answer, right? Is DSLs and compilers. The issue is that we've seen, you know, things, you know, past accelerators fail on many, many times is it can sort of do what I want, but my software does it just a little bit differently, and therefore it doesn't work, right? So, so I think we have to be careful in design. We're gonna have to work really hard to push adoption, you know, and sort of show the benefits to the community. And I think, you know, the move to sort of web-based access to scientific codes, which means we can control the version of the code behind that, will help a ton with that. You know, there are 2 tensions there are an average workflow lasts about 180 days, and an average domain-specific language for a particular device takes like 2 years to build, right? So if you say, I'm going to make this version of the GATK genomics pipeline work on my custom accelerator through my language, you know, by the time you bring it to market, they say, yeah, but now I want to run this other version, right? You know, so, and things die. So, you know, again, it's going to be picking the primitives, as Paolo mentioned, and it's going to be, you know, carefully designing those languages and getting buy-in from the community to use them. But you know, I think it's the only real answer is good libraries and good DSLs to do that. Because again, I don't think we can do, you know, if our space is everything you can express in a general purpose programming language, it's going to be impossible to optimize. But if we can constrain that space some, we can deal with more heterogeneous hardware and complexity. But, you know, the issue has been in the 30 years that I've been doing this, and in the 50 years we've been doing computational science, right? We've successfully introduced MPI and sort of OpenMP and nothing else. So, you know, AI may be the tipping point, right? TensorFlow becomes, you know, everything's expressed in TensorFlow or Torch, and then I only have 2 things I have to optimize. So, but, you know, history says it's hard, but it doesn't say it's impossible. So I think that's the direction we need to go. Mm-hmm.
Okay, thanks.
Okay, are there any more questions? Well, probably I'll just have just one question in the time we have left. Actually, it was in a bit similar way, I mean, a trend of, as Alejandro last question, because I think of course, with every evolution, I think AI can give a big contribution even for designing systems or even controlling the workflow, as you mentioned, for agent computing. This is actually concerned also in praise. So there is some work done. And I think one of the solutions for something that you mentioned, I mean, to be available data, is to have some kind of background processing. For instance, if you rely on satellite data, if you try to input it previously to the request, probably you can save something there. But these really complex things. I think you know very well because you're dealing with the hurricanes simulation and so on. But I think software question is really, really a fundamental one. And I know at least of an initiative in the UK that they tried to increment the software engineering part, not only in the university, but also to to have more people I mean, using that. And this is crucial because, and you know that for most open software stack is based on basically PhDs and the students and people in some scientific groups, they develop it and then the students change. So there is not really, and then as you said, to adapt to the current trends or modern trends is very difficult. So have you some thoughts about this? I mean, besides the question of having the proper tools and standardized tools, are there anything that you can make it develop institutional, let's say, to universities or the center, computing centers, even the government, if it is possible?
Yeah, and I think, you touch on, I completely agree with your comments, and you touch on many important problems. One that it's related to that software fragility problem is reproducibility, right? It calls into question, the credibility of science in a lot of ways, right? If we can't build reproducible, if our codes can't reproduce experiments because 2 years later the bin utils you're using has changed or the FFT library and you get a different answer, or nobody can run that analysis that was run for a paper, that's also a huge problem. And so, we're seeing containers are an element of dealing with that, and good provenance traces are an element of dealing with that. And you can imagine, again, we're going to need a cultural shift, and I'm much better at technology than cultural shifts, although that seems to be where the hard problems are. I'm both even more glad I didn't focus on those in my career, but we need to create a shift where these grad students do stuff and it goes into a repository with enough information for us to reproduce it. And this is where this notion of coevolution really starts to matter, right? Because if it's reproduced in a framework that runs in Java in a particular virtual machine on a laptop, it's never going to make the HPC world where it's going, right? And I already see this fork, right, between the applications that run on the Department of Energy systems in the US, where they have enormous resources and they're building, CUDA-specific kernels and 900 pragmas, right? And they have these very sophisticated code bases, and they run on, eventually the only codes that are going to run on those machines are those codes, and the codes that everybody else is building, Python and data science and containers, aren't going to even talk to those architectures, right? So we need to be careful in all of these efforts that we're doing this evolution together, right? We see what's coming in systems, we see what's required in scale at software, and that we build our, sort of engineering and software engineering and code management and reproducibility tools to fit that ecosystem, and they have to move in lockstep. And if they move independently, which sort of market spaces wants them to do, then there's going to be a lot of reinventing the wheel and a lot of innovation lost, and we're going to sort of stick where we are. We're not going to move forward as nearly as quickly as we could. So I think the coevolution of this is still the sort of key theme to make it happen.
I agree. Thank you very much. So are there any more questions from the audience? Your presentation has been really, really rich. I mean, lots of questions, lots of things that we, of course, could ask, but yeah.
Well, thank you very much. Appreciate everyone who stayed to listen.
It was really, it's really a problem to me to do the wrap up, but okay. So more or less, we still have some minutes, at least according to schedule. So just probably I just have a small question. So how do you see this? One of the things that you mentioned was this question with the Amazon and so on. So lots of discussion, of course, are related with HPC on the cloud, whether actually computer centers are still needed. Do you have any thoughts about that?
Yeah, well, given that I own one, the short answer is yes.
No, of course.
Yeah, so there's a longer answer, right? And that is, you know, to some extent, we were a cloud long before there was a cloud, right? These sort of campus level data centers, right? You know, it's not like users go in there to use the machines, right? They've always been remote access and fractional use. You know, I think what the cloud has brought, so there's a lot to learn from the commercial cloud, right? I think the notion of as a service, the notion of scaling through object store, there's been just tons of things we can transfer back. But again, it's still not tuned for science. And, you know, if you look at how we build and tune systems, you know, the basic building blocks are sort of the same, right? We're all using the same chips today, although specialization may change that over time. And I will tell you, model parallel AI is going to drive the cloud to look more like HPC. I'm relatively convinced of this, but today it doesn't. And if you look at the cost and the performance gaps, I mean, we can engineer for throughput, they have to engineer for uptime, right? You know, we can assume, you know, we are tuned to run large scale scientific codes, and they're tuned to do transaction-based commercial applications. And that tuning, you know, again, it's sort of optimizing in a design space, and it is enormously valuable in this case, right? In a perfect world, 10 years from now, of truly disaggregated pieces with, you know, building blocks in every rack of all the things and really fast interconnects between racks, then perhaps the systems will one day meet. Although I still think the HPC centers in government labs and in academia offer unique expertise in supporting the users and building these tools. And that will never go away. But right now, we've actually done a cost analysis of this. And, you know, we have at least an order of magnitude advantage in cost in building purpose-built and, you know, not needing 9 kinds of backup power for every system. You know, that is likely to somewhat converge over the coming decade, but I think it's at least a decade. And whether or not the solution that the market will drive them to will be optimal for science is still an open question. So, but right now, I think we have an enormous advantage. You know, we maybe need less per country because we can build them at scale or something like that and share them well. But again, the drive for interactive means lower utilization. The drive for more demand means more of them, right? I mean, the cloud's not big enough for all the things we want to do in science to some extent. You know, I think there's endless demand. So, you know, I don't see, you know, specialized scientific computing installations going away in the next 15 years or so.
Yeah, it was a provocative question. I know. Thank you.
Yeah. Well, I've thought about it a lot because I write at that justification for funding an awful lot. So, yeah.
Yeah. Also, some scientists or users sometimes come up with these questions. So that's yeah. What's the why don't you just buy time from the cloud? And
again, I would put your students through that exercise in the slide I showed. You know, hey, how much are you going to spend on this next workflow? You know, at the very least, we make sure you never run over the allocation we give you. Whereas the number of times I've had somebody call and say, so we had this grad student run up a $40,000 bill on Amazon last night. And we have no way to pay for it. And, you know, again, given that the average student, you know, you mentioned, grad students produce most of these codes and do a lot of this experimentation and runs. And if they can't tell you if the cost of a computation is between $16 and $218,000, do you really want them running on commercial cloud? So.
Okay, thank you again. So we are about time, about the end of the session. I don't know whether there's still or would be some questions from the attendees. I guess not. Yeah, so maybe I just do a quick wrap up. So, but anyway, before that, I really like to thank the two speakers, of course, and it's a pity that you cannot clap, or we have a virtual clap. I think Zoom allows that. But yeah, anyway, I think that's what wonderful presentations to the point, and I hope every attendee takes would profit a lot from these talks. I don't know. I think the session was, well, it was recorded. Sorry, but I guess that the presentation could be available as well. I don't know, but it's with the organizer because it's yeah. So of course you can also see and listen to the questions, but I think the presentations themselves would be also interesting to have. So yeah, so let me take as far as I can do some wrap up. Actually, Alejandro did the wrap up, I think, on the last slide, or not last, but before the last slide. So, but anyway, so it's I think, well, Alejandro talked basically about ARMS, so he described, of course, the importance of HPC for society. One thing he did not mention too much, but I think, well, it's behind all I think the ARM development, which is the lower power processors, which are of course very much used in cell phones and so on, and then how can be migrated to HPC. So in particular, it was the Mont-Blanc project was a pioneer in this regard, and since I was in Paris, I remember well, I was not in the work package, I said, this language regarding this, but anyway, it was already there, and the building of prototypes for ARM, and then Mont-Blanc is sort of a successful project, and then one of the consequences or the thing is actually mentioned in this EPI, the European Process Initiative, which builds on the ARM and as well as the RISC-V. So then it describes a lot of the implementations of MED. Sorry, ARM as this business model of licensing technology. It does not produce chips themselves, but then this allows a lot of companies to chip makers to do that according to some specifications. And of course, he cited several cases of this. One of the, of course, most notable is the Fugaku, so the chip based on Fujitsu's ARM. It's currently #1, so I think they are very effective from what I've seen in Limpak. So that I think speaks very good about the vector processing, because it's linear algebra, I think. So they are very efficient in this part. And then, so we mentioned several vendors which have implemented this. One, of course, was Fujitsu, then also HPE. There is some the company, the European company that is the SciPearl, which is set up to produce the Zeus chip. And then, of course, I think a big part of the talk was devoted to the SVE, so the scalable vector extension. And so he described in very much detail this. I mean, the possibility to have a variable length of vectors, and the usefulness of this, and also, and then the so-called vector length agnostic concept, which allows you to program independently of the vector length that you actually have in your vector processor. And this, of course, can present many advantages in the loops, and also the SVE predicates that allows you to deal with conditional instructions in a very efficient way. So you could really increase your throughput using this kind of technology. The support, of course, is very important, and to the availability of tools for supporting this new hardware. So it seems that already this has been done, or is been doing by at least the GNU compilers, and the support of this vectorization is already there, from what I have understood. Talking in the future, there is the support of this new data format, bfloat, and it's basically half precision float, but then with the different exponents, so the range is different, which would be useful for AI computations. Then of course, applying this to matrix multiplying, so implementing these BLAS routines with this new technology, SVE technology. And then the development of or porting of the libraries that you are very much used, of course, in HPC, like FTTW, LAPACK, and so on, and compilers. ARM develops already a suite for this, but they, as Alejandro mentioned, there is always some support from the GNU compilers and the effort. And in the end, so there are some debuggers already, so they are still working on that, but it looks promising. And then for the post-exascaling, so the packing of processors. So you have to increase, of course, well, the evolution of processors as base and as Dan mentioned, by increasing number of cores per socket. But one of the ways to increase that without too much big socket is to do some different packaging. And he mentioned that you can have packet in principle thousands of cores using, for instance, 3D scaling in packing. CP in packing sockets. I think I didn't miss much, but if I did, please. Yeah, it's okay. Good, thank you. Regarding the very complete and wide-ranging presentation by Dan, I can tell, of course, there's lots of things. I think besides, of course, again emphasizing the great importance of HPC, which actually is increasing, and they mentioned already this in other slides, that HPC has passed really beyond the traditional HPC, if you may call it, like using simulation data, using for a certain type of scientists and scientific research, to encompass also data science and data processing. This was really a trend for the field for these past years, and it opens a lot of new opportunities and challenges for HPC. Also, the scope of HPC then was very enlarged. I can comment on this briefly because one of the, and you know, this big CERN, as a big research institution, has pushed for many years the concept of grid computing, which basically high throughput computing, and several computers scattered all around, and was for some time this was an effective thing. But now they really turned for HPC. So due to the evolution of hardware and software and storage, in the end they have been deciding that they are moving in that way. It's clear now that they do that. So the HPC really is starting to be everywhere, let's say. So because it includes all those this kind of computing, data processing, and so on. So we described, of course, the new systems, in particular Frontera, and the way it is done. The challenges of installation, of course, a very big computer in this way, and in particular, and then then it turned to what science is done on Frontera. And Frontera, of course, it's by its flexibility, and one of the things which is you may consider advantage is basically a CPU system. I think you have GPUs for visualization, some kind of processing, but the main system is based CPU core, not. So it's not like other system, big system, US system, also European systems, for instance, Switzerland, which is the same. So it allows, I think, advantage a big flexibility, and so it can run simulations. Large simulation cannot be done in other kind of systems. So that's an advantage of Frontera. And then I talked about several data science cases. And of course, one of them, which is very important right now, is from the coronavirus simulations. So there is a US consortium. They use basically molecular simulation based on AMD. And of course, discovered something that is already discovered based on simulation Frontera. But then, of course, again, there's in TACC you have the advantage of also coupling this with other kind of processing, basically machine learning and artificial intelligence. So coupling to the high number of cores that you have available, CPU, the pure CPU core that you have to do the simulation, you can add this extra processing, data processing, which of course is important also to to perform this simulation. And then you have a collaboration with Summit, with the Oak Ridge, which has the Summit, which is based basically on GPUs. Mentioned already, one of the things, of course, is the POSIX file system. So the importance of file systems and the I/O. I think this, from my point of view, it was some experience I have already also here in a much smaller scale, is I/O is crucial for these systems. And I think is probably one big advantage also, no, I think even the cloud, but that's why some other, this kind of, sorry, institutions like CERN are going to HPC, because you can really have in some place lots of computing power, lots of storage with a fast interconnect. And this is really a big advantage to process high volumes of data. So you mentioned also, of course, the Python, so the other workflows that you currently have. So we have to go beyond the traditional, let's say, the HPC simulation based on C on Fortran. Regarding to this, you mentioned, and then I skip to the end, the question of having, this is an important thing to have containers from some processes. Containers are a bit are not easy to maintain, but I hope that you can devise some way of integrating them, sorry, more easily into an HPC data flow. By the way, I can comment that in Praise, people are looking at that as well. I think, from my knowledge, containers are not used in the large scale computing, small, but they nevertheless, with the small scale that allow, they can have this flexibility that is very important for some users. So not at least that's what I've been learning, and you mentioned this. Regarding future technology and the state of technology. So you mentioned the end of Moore's law. So this is a trend which has been there for some years already. So that you cannot increase frequency. You can increase, or you are increasing number of cores per chip, but then you have some problems in this regard as well. If you go down to features reduction in chips, then you have trouble again. So you can do it, but probably and there is some limitations. People are trying to go this way. Then, of course, a very important problem, because you have now so many cores in one chip, is the memory access, memory bandwidth. And this can be addressed by this high bandwidth memory, which promises to at least to close a little bit this gap, to have the memory bandwidth within the sockets. Then, of course, you have, let me see if I have this, yeah. One of the things that you mentioned, actually discussed right now with just a moment ago with Alejandro, was this interconnect. So the idea is relating, of course, to the memory access, in which you have this new technologies, silicon photonic and so on, that allows you to, in a chip or in a node, to have to address these problems and to even dynamically reconfigure a node. So that is a really interesting, so what we call this disaggregation, if I'm not mistaken. So the idea that you can reconfigure a node to serve several purposes. It's not like today, in which you have several kinds of nodes to serve to different types of computing. If you have this flexibility, then you can probably address this in a better way. Of course, then you have the so this is related to the other problem or the issue, it is general purpose versus specialization, right? So if you can have, or could have some, thanks to new hardware and to interconnects and so on, possibility to reconfigure a node to serve several different purposes, that would be, of course, very nice. Regarding the software development, of course, then this is a big problem again. Because the software development takes lags very much, of course, the development hardware. So, and this is connected with the discussion we had just a minute ago. So we'll have to, it's expensive, it takes time. So it would be useful if you, well, this is a problem to be addressed as well. And it's related with tools, to availability of tools, and also to the existence of software, new software engineering questions, let's say. Other yeah, in the end, we talked a little bit about also there is new trends, quantum computing, other things that are still developing. It's not clear what will come out of it. This is a new algorithm. I know there are simulations of quantum computers, but in classical hardware. But to have increasing quantum computers, this is very hard, right? Because you have to have a special, well, cooling until the zero, the absolute zero, and so on. So that you have very special hardware for it. It is promising, but it's a lot of work to be done. There is big, even in Europe, there are also big initiatives, a flagship program for quantum computing. But people actually are working, or the Commission, the European Commission, is interested in having seeing the connection or possible connection between HPC and quantum computing. Let's see if it is possible. But so they want to involve computer centers in this effort. But from what I've seen, and I think you mentioned, this is not yet done, and maybe will take some years until there is something there. And then in the end, you mentioned HPC versus cloud, which you already discussed a little bit. And then, of course, there is this the connection between software development and complexity in hardware that you mentioned. So that the adjusting between the software development and and hardware development and complexity of hardware. So several hardware configurations, and then to adapt the software to it. One of the things, of course, that you can use are containers, which can address a little bit the flexibility or the complexity of hardware and hiding this complexity to the user. But then you have a maintenance problem. Okay, you have to maintain a lot of versions, so it's not easy unless you try to use it in a sort of more independent way, or not relying on very particular libraries, but if I understood it well, to be more general, or at least to have some kind of standards, or to not to be very particular in what you put in a container, to have a more general setting that allows you to not having such a big maintenance effort for containers. And then in the end, you talked, I think, a very interesting and very forward-looking project, which is this DARPA project, in which you could have deal with this diversity of environments and software by having a machine, and also workflows. Of course, this is very important, because the traditional using of HPC by having some session, SSH session, and then just submitting your jobs to a queue and so on, cannot be done with kinds of version computing, which is, for instance, for tackling these catastrophic events like tornadoes and floods and so on, tsunamis. So the idea that you can have eventually some interface with the user, and this can be done, from what I understand, with the machine learning or AI, by having some machine doing the sort of pre-processing and then submitting in the end to an HPC machine for doing the job, and then the input and output can be as simple as some English statements in the Google Doc, and the output, I think, would be in the same format or something like that. So that will be something else. So it's very interesting. So this, if you can really do that, but I think it is already, we have seen this already. I know some projects or some people, for instance, with some people, not really cloud users, but for instance, from the biosciences in general, that are used really to use portals or some submission through a web browser or something. So that devising a good interface with your HPC system and easy to use, it's a challenge, but it has to be addressed. So probably in the end, you have this kind of an interface, a machine who can do that, to do the interface with user with an HPC, and yeah. So that would be using some tools like so artificial intelligence, whatever, machine learning. But yeah, that would be probably a future trend. I don't know if I missed. Probably I missed something. You talked so much. Yeah. So yeah, you mentioned also this is a multi-physics. So this is again the diversity of kind of computing, edge computing, multi-physics, multi-scale. So to address this, the other thing that you mentioned, I think it's called also ensemble computation. Then that you have to quantify uncertainty, so you have to have a lot of runs with the same simulation, which can be in itself a very big simulation. So that this is also a justification for exascale machines, from what I know. So it's a lot of this, of course, poses some problem again in the workings of the software stack, of the HPC software stack as well, and how you interact with the HPC system. Anyway, if I can sum it up, I think the future for HPC looks bright but challenging. So lots of things are going on in hardware and software, but HPC remains, I think, even more a crucial technology for science and society. If I make sum it up like that. If I left something out, please tell me. I don't know. I took some notes, but probably I didn't cover everything.
I think those hit the main points.
Yep, I agree.
Okay, good. Thank you. So I think you may end the session. So again, I think there are some claps here. You can clap. But anyway, I think in a virtual clap, I think it was very good, a very interesting and very session. And I think that all the material will be available to the participants and other participants probably, because I think there's a lot of an HPC community in Portugal will benefit from that. So at least in the contacts I have, network I have, I will make sure that I will send out and tell about this session. So
thanks very much, Pedro.
Thank you very much.
Thanks, Alejandro.
Alejandro and Dan and all.
Thank you, Dan. Thank you,
and I don't know whether from the hosts, I don't know whether it will be the host that will end the session or it could be, or those are here, I think.
Yeah, I will end the session.
Okay.
Thank you very much and goodbye.
Thank you very much.
Thank you so much.
Thanks.
Thank you.
Bye.
Bye-bye.